have a private meeting with Institute students and their executive session, because you guys have work to do. Then you'll come back and meet with us, and then we're going to have separate dinners so you can talk about us. We can talk about the other things meeting. Tomorrow, we again, you're going to provide us with questions. We're going to work on the responses tonight, on the answers to those. We meet again and respond to those questions. You're going to have a meeting with the dean tomorrow morning, the NSF folks. It's worth noting that Rajesh, the meeting tomorrow is in a different location. We have to get you over from the dean to this beautiful, actually, place in Duke Forest. It's not it's in the forest, but it's not camping. You'll see it's a beautiful center. We'll have the morning session. And then for all the folks who are in the Athena Institute, we're having a team science workshop led by Rebecca well, Rebecca, you were at the December meeting. So Michelle Bennett, who did that amazing team science mini workshop at the December meeting, she's come here and she's going to work with our leads to help us build synergy amongst the groups. Okay, one last thing. I'd also like to welcome the folks online. I don't see the org chart in this. That's it for this. But let me just introduce the pillar leads. They're sitting. You can raise your hand. Lin Zong. People will know these folks already. Suman, Michael, Daniel. Sorry, Daniel, and who else am I missing? I don't see the org chart here, so well, of course, Yoran. I think I'll let Yoran take it over here. There's no, there's. Yeah, the org chart is missing from here. Oh, okay, there we go.
I told you it's there.
Okay, here we are. This is this. Who have I missed? Miroslav. Where's Miroslav? Miroslav Pajek is our other lead. I didn't see him in the. He will be here, and I think I've been else for memory. And let me, without further ado, introduce Yoran, the PI, and give you an overview. Well, no, actually, sorry, Alex, and then Alex can introduce the.
Good morning. So this org chart's not helpful for me to introduce my cohort, but glad to see so many of you in three-dimensional land. That's very cool. It's been the Brady Bunch kind of meetings until recently. So glad to be here. So my name is Alex Jones. I am in the Computer Systems Research Cluster at NSF, and I'm the lead program officer, the interface with Athena at NSF side. So with us we have Rebecca Hua, who is a co-lead for the AI Institute's program, and we're glad to have her here with us to help make sure we follow all the rules and do all the right things. I saw Ching Wu is online joining us from an unspecified location on the West Coast. Ching is from Air Force Research Labs and is an expert in AI, and so we're glad to have him as part of the NSF cohort. Also, Yingying or Jennifer Chen from Rutgers, chair of ECE, right? Chair of ECE at Rutgers University, and Sammy Khan, also a chair at Mississippi State in ECE, and also a former colleague of mine at NSF that are here joining. So you'll notice we're all rotators. None of us are permanent NSF employees, so we're all scientists like you. So we're going to try and be friendly and also be evaluative and helpful. So our goal is to learn and to help in any way that we can to make Athena successful. you guys are, in terms of computer systems research, the pillar of the AI effort that we sponsor as part of our portfolio. So we look to you not only for interaction, but also for leadership of our community, for the other PIs that do research in AI, machine learning, and edge kind of topics, to be kind of the leaders and people that we can point to and say, you know, these are the people that you should talk to about ideas and that. So, again, excited to see what you have planned for us, and that I'll hand it over to Iran, I think is the next person, so thanks so much.
So let me switch to my slides. Right. I have a large file size, so okay. So first of all, you know, as the director and also the PI of Athena, I welcome everyone here, including the NSF program directors, you know, the evaluators, all the PIs, students, other researchers. So welcome to do our second annual review. My name is Yan Chen. I'm actually the PI and the director of this AI Institute. So people remember, you know, back to 3 years ago, we started put everything together, submit a proposal, go through all the review process, you know, was granted, and also we start doing jobs. So today I want to give the annual review for the second year, so which is called the AI Power Edge Computing. Before we start, you know, everything, I want to share our perspective about the edge computing. I know people have very different aspects about this edge computing from all the different angles. So for example, people can partition the edge computing from different layers, such as, you know, the cloud computing, the edge data centers, the edge devices, and also have some communication layers in between. If we look at those partitions, we actually decouple the computation from the communications. Basically, need to consider individually and create the difficulties for cross-layer optimization. It's actually not new. We know this for many years. We revisit, you know, this view, and we feel like we should actually somehow interpret edge computing from a broader and more computing perspective. We consider the edge computing system as a global connected computing system, which is going to link the computing nodes, which are defined by the local computing, as we actually design the edge devices. Also, we need to create the collaborative computing across all the devices, and also the devices with the edge data center and even the cloud. We also need to connect them, including the both compute and the data, because everything is about how to obtain the data and process the data in a collaborative way. We will show you later on how we can do this in a more collaborative manners. And also, finally, we need to protect those data because there are huge, you know, privacy, security, safety concerns as we're going to deal with, you know, large number of the data and also with the larger varieties. That being said, we need to handle we need to propose a unified compute-centric view of the edge computing system, which is very different from what we have seen in the past. This is actually the all new view of this AI Institute as it is a foundation to serve this research project. We're going to enable both vertical, which means across layer, and horizontal, which is cross-node optimization by considering a lot of heterogeneities in the device and also in the data. And also, finally, we need to place the artificial intelligence to serve as a foundation of defining and executing those strategies. So our view will be the global computing system. And you're going to hear, the talks from our PIs, how they can implement this on this unique but also novel perspective. And our goal is going to build a highly scalable, efficient, and also robust edge computing system powered by the AI technology. That's why we have another short talk after we talk all the pillars about the foundation of the AI and how AI can benefit this one, and how our research is going to advance the research of AI. We also identify 4 task forces in the year 1, if you still remember, as I presented last year, by following the 4 major challenges: data and computer connectivity, data protection, collaborative computing, and local computing. Those task forces may change dynamically, but at least in the year 1 and year 2, we want to build up the intelligent connected system. We want to develop the federated learning technologies, and also working on the efficiency of the whole system, and finally, to handle the requirements of the security and assurance of this whole computing system. On top of this, form our research tasks into 9 focus areas, which will also show up in our last year report from different domains defined by these 4 task forces. I'm not going to read one by one for this, but you can roughly tell how we try to integrate our research efforts from all these PIs into these 9 focus areas. After we formed this in the year 1, we realized some levels of the integration of our research project efforts does not really give us the ultimate goal or something we can demonstrate to NSF about how we are able to also integrate the technologies we're going to develop to something bigger, more comprehensive, and more impactful. So that means that, after we develop this technology, we still want to have something which is more demonstrable and to show the joint efforts of all the PIs, because we have more than 25 PIs here. So we defined the 3 pillars, as you're going to see in today's talks. Number 1, we're going to build up the edge-powered AI system, including both the hardware and also the AI technologies, to provide the foundation of the computing to serve all our research on edge computing from the both sides. On top of this, there are 2 pillars, namely the collaborative XR and the collaborative situational awareness and autonomy, to handle 2 major challenges of the edge computing, which are the data processing at the edge and also decision making at the edge. So those are the 2 major tasks you're going to see at the edge. And we will link these 3 pillars, which are more demonstratable goals, with the 4 task forces in the year 1, year 2, and the 9 focus areas, which consolidates, the research efforts of all our PIs. Those are the relationship between all of this. And of course, it's the AI Institute. So we're going to build up the foundation of the AI, which is going to play a very comprehensive and deep role across all these efforts. Okay, so for the edge-powered AI system, and also for the collaborative XR, and also the situational awareness and autonomy, we will particularly handle the functionality, efficiency, heterogeneity, and trustworthiness when we are developing the foundation for the edge-powered AI system. And we're going to also handle the efficiency, availability, and security for the edge, system to serve the services and application innovations. So those are the relationships between the 3 pillars. and also how those can link our goals developed by some other task forces. The pillar one will be the edge power AI system. So later on, Professor Lin Zhong is going to present more details. So I just want to show a rough high-level overview here to say if we have edge devices and also the edge data center, how those going to coordinate each other to provide different applications, different technology to support the edge computing space, and from many aspects which we listed here. So from the federal learning technology to the tiny ML, to the security, fairness, or efficiency, so on the first. So there were many PIs are working together and also collaborating closely on the different components. So later on. So Lin will talk more details about this. Also for pillar two, collaborative XR, we have a couple applications identified. This application may change later on, but currently for the AI for public, safety, and also for the VR for education, because we identify those are the two probably critical applications, with our efforts on edge computing, and to deal with the challenges, including the heterogeneity, the real-time and energy constraints, and also assurance and reliability. So there are also, the collaborative efforts, from 6 or 7 units where we're working together on this, and also Suman will talk more details about this. And we have a pillar 3, which is a collaborative and situational awareness and autonomy, and the goal is to utilize basically heterogeneous based computation and sensing for assuring robust and resilient autonomy and situational awareness system at the edge, even in the contested and highly uncertain environments. This actually more from decision making, but not traditional data processing. You will hear from Miroslav about how this is going to innovate the future applications of edge AI by enhancing the AI capability of the edge devices. There are some applications that he can talk about, and there are many researchers are working together on this particular pillar. You will see actually the same faces show up in maybe more than one pillar, which is very natural. That basically means, the research of those PI actually going to cross the multiple pillars. Actually, that's something we try to encourage, but hopefully we don't overwhelm our PIs. Okay. So having a technology roadmap is just not about solving the problems. We want to have a bigger picture about what we're trying to achieve in this 5 years and what we can accomplish or we can predict after this 5 years. So year one, in the past year one, we actually try to focus on the innovation of each focus areas, which are the 9 we just show here, and also the PIs. Because they are the world-class researchers, I never worry about they can deliver, also the world-class research. But that's not sufficient because, we receive this grant, we want to build up something more than just 25 smaller grants, right? So we actually work very hard in the year 2 trying to consolidate those ideas to task force and the pillar. But basically, later on, we can show this. The talks we will show how we are able to consolidate those ideas and to make sure we can have strong synergy between the different research of those PIs, and we'll see how they can engage between each other. In year 3, the coming years, we're going to integrate all these ideas and towards our ultimate goal, and to show people that those kind of ideas are collaborative and are going to integrate together to show our comprehensive demonstration of those ideas and technologies, which is more influential than simple sum of all this. Therefore, we'll demonstrate the teamwork by integrating this innovation. So you will see actually something bigger at the system level to show these technologies which we develop will be able to demonstrate to the industry and the whole academia about something they can never foresee or even imagine from 4 years ago. Why? We'll find out actually we did not stop at the demonstration. The majority of people for the demonstration evaluation last year, but I think that's not sufficient. We need to look forward. So in year 5, we'll define the industrial standards and also future edge computing technology roadmap. That's going to conclude, what we will try to accomplish in this 5-year project and open up the new era of the next 5 years, which means we want to run with the technology of edge computing with efforts of this 25 or 30 world-class PIs, also the AI Institute on this one. But of course, there are many other things that are ongoing. That's not really mean we're just only focusing on integration or demonstration or defining. It's just some critical mission we're trying to achieve, year by year. But I'm open to any questions you may have. Okay, so also we have other component, to further enhance the inference, also the broader impact of this AI Institute, on top of this research. We have education and workforce development. We have very strong the EWD team working together trying to enhance the broader impact of the AI Institute. This afternoon, you will hear from them. And we have a very strong team on the broadening participation team, the BP, to work with many non-profitable organizations on this support efforts. And we also have, the collaboration and the knowledge transfer efforts to commercialize and transfer our technology developed by our AI Institute. Actually, we have one PI. He already sold his company last month. We'll talk about this one later on, which actually has a very relevant, technology developed by this AI Institute. So those are, all our PIs. So you can see we actually did some adjustment of our PIs, dynamically. I think we'll continue doing that to make sure, we can align with our efforts and also make sure they can work together. So now we have this basically 31, the PIs we have, including the 3 international collaborators across basically 11 universities, 3. And we have very healthy composition in terms of their background, the expertise also on the first, and also the career phases. And this will be our, anybody can put the banner here? Remove this, I don't. Or? Yeah, we have a management, and it's not planned. Basically, it's a mechanism. So we have for management and integration mechanism, to handle all our management challenges, including PI, this is my personal responsibility, and also the pillar list, the project list, which basically our PIs, and also the management team, including the Jeff, who is our every time I need to redo it. It's not intelligent at all. So, and management team, the Jeff, who is our deputy directors, and together with Rajesh to help me to handle all this, logistic and administrative challenges. I have our impacted list, to work on the EWD, BP, and also operations on the first, and also our external stakeholders, including our external advisory board, industrial liaisons, also some public, collaborators, to handle all other broader impact, We have a very thorough and strict, evaluation access, mechanism. So we have a weekly report provided by all the PIs and also the pillar leads and submitted to monthly pillar meetings, with all the PIs, to discuss the ongoing efforts and collaborations led by the pillar leads. We have a quarterly PI meetings and also the report submitted to NSF, which is a more detailed report, including all those research highlights, the data, so on and first. And we had our annual review meeting last year around the same time, April actually. And we have a tech showcase last year in August. There are more than 100 people show up, even during the pandemic, in person, to show people, our research, innovation. That's why I mentioned the innovation of all the PIs. We have our internal review in the March, and we invited external reviewers to join our internal review to provide the impact to our comments to all our PIs. And we will provide our comments to all the PIs and by the leadership team also. And we have this annual review meeting. Those are some, photos of we actually talk, during the different evaluation process. Our internal review asked all the PIs to present in 2 half-day internal online review, the March 21 and 22. 3 external reviewers, including 2 former NSF program directors and also the 1 very experienced, evaluators, join our review and provide a written review. And they actually also, comment in the real time during the review meeting. And we have a pillar list, communicated with individual PIs about the feedback and incitation to change. Our criteria, including the innovation, the innovative, quantitative, you do have quantitative measurement of your research, not just the quantitative, and also the potential in terms of the technical wise and also the societal wise. And also if you have sufficient collaborations, and synergy between the pillars and the PIs, and also between the PIs. This will be very important for criteria when we actually ask the evaluator to provide the inputs. And based on this, those are some more detailed questions we ask our PIs, including the technical work, innovative and achievable, or if the quantitative the metrics has been used, to evaluate, this research, not just number of the papers, and also the significant potential for societal impact in the form of the commercial, government, or nonprofits on the first. Also, by collaboration between the researchers and also the pillars. We require every single PI to associate it with at least 1 pillars and to join this monthly meeting and also show us the evidence about the engagement. What's going to happen if they fail or we identify something they need to improve during the review? So all the PIs will receive a formal review, even we already communicated with the PIs, by the pillar list. But we're going to provide you formal reviews after this annual review meeting, which combines the comments from the Athena leadership teams and the external reviewers. You will receive a formal review from us. Please be ready for it. The PI who needs special attention, I use the words, will receive a detailed guidance about how to improve and will be given a 4-month probation time. So I believe you want to pay attention to this. Another internal review will be performed by end of August or early September for those PIs. And remember, there'll be some documents, or works you need to do, including submit a report and maybe some presentation. This, to show you make some change. And if the PI passed the aforementioned internal review, I mean, end of August or early September, a 4-month fund of the third year will be released to the PI. So starting from the year 3, we're not going to automatically release your fund. There are a couple criteria you need to meet.
Approaching Fenway,
Including-
for bus connection. Doors will open on the right.
Including satisfying the review, both internal and external reviews of Athena, and also the spending rate of your grant, which means if you underspend, you're not going to receive year 3 fund.
This is Fenway. The destination of this train is Riverside.
And all the PIs will have a semi-annual review by end of the 2023, all the PIs, not just the PI who need a special attention. If the PI pass the review, the rest of the third year fund will be released. By the way, if you pass, this year 2 review, you automatically release by year 3 if your spending rate is above the bar. But for other PIs, rest of the year 3 fund will be released. So this policy will be implemented, and hopefully this will give the people some opportunities to think about how we can better align with the SAI Institute and also engage with our PIs, also contribute in a more collaborative way. So we are lucky to have the international collaborations by support of the NSF to engage with 3 universities, including the BGU, the EPFL, and also from Israel, Switzerland, and Germany, working on something were originally not in the scope of the AI Institute, but we try to expand by leveraging the expertise from those universities. Those are the PIs, from those universities, including everything to the vehicle communication for smart cities, or the medical federated learning, and also some perception neural network acceleration. So they already, have some accomplishments, to be published, also some ongoing efforts. I'm not going to go into the details, but every ongoing effort. And there are going to be some workshops, to include those international collaborators to join us. They are not able to join us for this particular review, but they can join us in the tech showcase.
Approaching Longwood. Doors will open on the right.
So we pay special efforts on the community building. We work very closely with some organizations, especially in this particular case, the European organization, like the Next Generation.
This is Longwood. The destination of this train is Riverside.
Someone. Can you help me to mute someone?
Yes, if the call-in number could please mute, the call-in from area code 919, if you could please mute your phone. So
we just signed the MOU with Next Generation Internet, enricher program from European Union. They're going to send, their researchers, to Duke, to work with our researchers on the relevant research projects. And they're going to pay for it. By the way, we don't pay for it. It's a good thing. And also we just submitted, the EU-US collaborative proposal to the EU for the Horizon for the next generation our network and the services, and the Tingjun is the lead from that. It's also the joint product with, tens of millions of dollars, euros, I would say. So we have, the many seminars, has been done, which every month or even more frequently, they're going to present, the work from our AI Institute, or, some invited speakers. And those are, working with the 3 organizations, the Inspiring Minds, the Knox Street and the Studios, and the Wicker group, to work on the broader impact and the the broadening participation efforts in this afternoon. Sunny and her team will talk about this. So no wonder, I don't think this will be our main focuses, but I still want to show some data of this AI Institute. Obviously, they publish a lot of papers in the very top venues, and there are more than 30 talks that are given by our members, across all the conferences and even different countries. And we have 5 invention disclosures have been submitted by our PIs. We have 12 seminars, today. We have 5 undergrad students working with us in the coming summer, and we also engage with more than students and postdocs. Supported by our AIE Institute. So technology transfer and entrepreneurship, those are the 5 disclosures our PI submitted from different universities. And I just mentioned that, one of our PIs, basically Song Han from MIT, he just sold his company to NVIDIA, working on the TinyML, which is also the scope of the Athena. And, his postdoc will talk about this research, this more. Okay, so we have external advisory board. They play a very important role to advise us, about how we can perform the research and the collaboration with the industry, and give us the comments, to our research, including, the representative from the industry, like Microsoft, Qualcomm, Motorola, Samsung, and also the funding agency, industry funding agency, ISRC, which is local. And also international, the nanny from the EPIFL, who is leading the joint, center in Switzerland. I will stop here, I think. So I will open for any question you may have before we start the pillar talk. Or we can save you questions, after some of our pillar list to present. Let's do it. Thank you so much. Yeah.
Morning. Thank you for coming to the annual review of Athena Institute. My name is Lin. I'm professor of computer science with Yale University. I'm going to talk about fun stuff, the after events. So, what happened? 2 keys on the mouse. Keyboard work. Right. Okay. So the world of AI changed so fast, right? When we're writing the proposal, writing the proposal, GPT was still in development, right? So what happened in the last 2 years, GPT, large language model, ChatGPT, has become so powerful and demonstrate a lot of possibility. So that has heavily influenced our thinking. Right? We had, with also the edge devices, like IoT devices, AR, VR devices, surveillance cameras, also driving cars, the resource constraints. How can we bring the power of large language vision model to such resource constraints? And in this picture, basically, I think today you will see Miroslav and Suman will talk about their kind of a application-driven vision, like AR, VR devices powered by edge data center, or drones, flying drones, latency-sensitive devices powered by edge data centers. Similarly, when we talk with industry partners at Motorola Solutions, they have surveillance camera in schools. They have one WinP server in the school, and they would like to track and manage shooters, right? Like also bring AI to the surveillance to make life-critical decisions in real time. So the challenge we in this period collectively try to address is how to enable large models in small data centers, serve potentially massive number of resource conservation. The research will, we will actually, Miroslav's team and my group have been actually working on a research testbed and demo in which multiple drones basically have their computer vision empowered from a small data center running in Yale. So I think that if you go to the poster session, you try to find our poster, and hopefully they have the drone. I don't know whether they have a drone there, but Miroslav will show a video of that. This testbed demo kind of, we use that as internal testbed to help evaluate some of the research idea, also drive collaborations between multiple. Now, let's look at this, this landscape from a system perspective. On the left is the picture. You can see what is system challenges on the edge devices, resource. On the right, you will see the whole stack of challenges we tackle in the edge system. In this, Mizan already showed the picture. Like in this period, we actively collaborate ways working together. But in this presentation, I will focus on the work on the right side. When Miroslav and Suman they talk, I think they will cover some of the research happen closer to the end app. So to begin with, I think the first things top down from the stack is the availability, right? A small data center, edge data center is small, therefore has lower hardware redundancy. So when one component fails, the failure could be catastrophic. And therefore, Krish and Daniel, and we have been looking to how to use machine learning to predict the faults, potential hardware faults happening in different components, and then preemptively recover from the faults, therefore to improve the whole data center's performance. And on the other hand, because this small edge data center can potentially serve a large number of IoT devices, which are resource constraints and therefore are prone to be compromised. As back in 2016, you probably have heard of MiroBot-led attack DYN.com. So how can we detect this ROG edge devices from the perspective of edge data center? That's Mike Reeder's research. So the whole idea about verification, which combines symbolic execution and machine learning to be able to tell good devices and bad devices. Let's move down the stack. I'd like to talk about how can we run machine learning DNN model inference as a service. So today, if you look into large data centers, the requests for DNN inference come into stream. And the service typically group the request into streams based on the latency requirement, which model they use. Basically, the same model, same latency requirement request can perform this. You could have a large number of streams coming, with millions of streams. On the other hand, you have a cluster of GPUs, and it's hundreds of GPUs out there. You basically have to try to utilize the GPU to serve all the streams latency requirements. There's three things that matters: scalability. You want to support as many streams as possible and utilize as many GPU as possible. For two good put, that means the request that's served per second that meeting the latency requirement, right? So any late response basically doesn't count. The customer wouldn't pay you. And number three, utilization. You like to keep your GPU busy, right? So existing systems have difficulty achieving all three at the same time, often have to make hard decisions. So my colleague Anurag in the last year has some very important results in improving the DNN as a service, inference service, in small data centers. The idea is to group streams into groups based on their how predictable their model performance model is. Therefore, although the stream is not that predictable, the arrival request is not that predictable, but if you put them together, they actually become. Talk to him. The second key idea is you decouple from provisioning. As shown in this picture, you have periodic planner called HERT. Basically, periodically examine the coming stream and decide which stream to group into the same group. And then for each group, you allocate a certain number of GPUs. And then the second step, the real-time online, the Flex, which is the online scheduler, that will try to schedule the request to the GPUs. Using this design, the Shepard is able to achieve all three goals: a high throughput, high utilization, and also high variety. And here the results show Shepard beat reported. So after Anurag's success, basically now the Shepard was done with just single task DNN model, and with the increasing prominence and also promise of large language models, vision models, we're looking to how this kind of multi-semantic models, large models, can be served from a small data center to a large number of users at the same time. Imagine in Durand, you have a small data center that serves all the drones running using the large language model as a backend. That's something that Olga, Anurag, and I have been discussing recently, and we have people from Google and Motorola Solutions reach out to me. As I mentioned, for Motorola Solutions, they particularly care about in a high school setting, you have, let's say, tens of surveillance cameras with small servers, but they would like to leverage large language vision model to do things that matters for a very interesting and personally very motivational application. Hopefully next year we'll have some exciting results. So let's move down the stack. I want to talk about once we talk about DNN as a service, then let's look at more fundamental issue about how the data center is architected and how the resources are organized. Anurag, again, my colleague from Yale, has adopted this cool idea of resource disaggregation. Basically, instead of aggregate resource by servers, rather you have blades of memory, blades of actuator, blades of storage, and all these blades are integrated overlaid. Through this, you can achieve even higher utilization of more flexibility of allocate different type of resources. So we have made last year we talked about the operating system called in-network memory management for this distributed data center. In the past year, we have made more interesting advancement of this design. For example, to support concurrent locks efficiently, to support distributed point chasing in the distributed data center. All this work basically lays the foundation for us to run large-scale concurrent AI workloads on top of a small edge. So we have multiple posters on the threads, so check. We move down the stack. So it's well-known actuators, specialized hardware is key for the efficiency. Therefore, I'd like to hand the podium to my colleague, Lisa, and then Abhishek can talk about their work on actuator design and their system support for the edge.
Hi, I'm Lisa Wu Wills. I am an assistant at Duke University, and I'm going to focus my talk on how we can collaborate with my research group with Lynn and Miroslav's group to solve their problems of having to train and also use many independent CNNs and DNNs to perform computer vision tasks. So our team is going to be architecting a multitask vision transformer for Edge Data Center. So from what Lynn just talked about, you saw that different vision tasks, such as maybe gesture recognition or pose estimation, they are done on separate CNNs. And in fact, state-of-the-art machine learning models that are great at these tasks are well-trained CNNs. And specifically, the ones that we're using now is the Google MediaPipe and also the PoseNet. So, sorry, I'm just adjusting to what I had and then what they're putting on here. So the problem of having independent CNNs to perform each vision task is that every time we want to add a new, model, the new model needs to be trained and also deployed. And another thing is, even when we try to do them on the edge inference, each model is not power efficient enough to be deployed on the edge devices by themselves. So what happens is we want to do them in the edge data center, but with edge data center, it's not scalable if you have multiple CNN models that you need to put the request through and then get the responses. So our approach to solve this problem is threefold. So the first one is to provide a solution that has software, that's a software solution that provides efficiency. So we want to use one vision transformer model to replace multiple CNN models. And like I said, the MediaPipe and the PoseNet are the ones that we're going to start with, which is Google open source, very well-trained CNN models. And the second approach we're going to do is to specific training using this ML technique called knowledge distillation. We want to transfer the knowledge from these already trained state-of-the-art CNN models into this vision transformer that we're working on. And the third approach is a software hardware co-designed vision transformer accelerator that's going to provide better performance and much better power efficiency. And the way we do this is based on this BERT transformer that was already architected last year and published at ASPLOS. And today I'm going to focus more of my talk on the deep dive into the architecture. So briefly go over the first approach on providing efficiency. We want to use one vision transformer model to replace multiple state-of-the-art CNN models. And the reason why that's more efficient is from recent work that's showing you can take vision transformer models and train them from scratch on ImageNet. And if you see this IT, which was published in 2021, you can actually get a smaller model size using less number of max, but achieving higher accuracy compared to, let's say, ResNet. Another way to provide efficiency is that when we use vision transformer models, they're actually trained in two different steps. The first step is pre-training. Second step is fine-tuning. And why this is good is because in the pre-training phase, you can actually pre-train a large vision transformer model with unsupervised learning. So that means you can actually use a large set of images that's unlabeled and available in the wild. And after that, you can just use a much lighter weight fine-tuning to change the parameters of perhaps just one layer of the model at the transformer and then also with a classifier at the end. And this can be done with a much smaller data set. So in this edge drone data center scenario that we probably just need to train it with labeled data set with gestures, for example. And then this vision transformer model would be able to perform just as well as if you have separate CNN. So the second approach that we're talking about is training using knowledge distillation. So we don't want to have to retrain the vision transformer from scratch. So what we want to do is we want to take the models that's already trained by Google, which is Media Python PostNet. We want to transfer the knowledge that's in that model into the vision transformer that we want to deploy. Okay. So this avoids having to collect lots of data to train the models from scratch, but we just transfer the knowledge that's already been done. Okay. So now I'm going to focus on the microarchitecture and also the novelty and the efficiencies of this hardware-software co-designed accelerator, which is a BERT transformer that our vision transformer is going to be based on. So the accelerator actually is able to achieve 7 times better speed up and 48 times more power efficient than one A100 GPU card. And this picture I'm trying to show here is plotting number of inferences per second per watt on the y-axis, which is a measurement for power efficiency, and then the input sequence length on the x-axis, which is number of tokens. So what you can see is this blue line is our accelerator, and notice that the y-axis is actually a log scaled axis. So the red is A100, the greens are the VPUs. So when you see these plots, what it's showing you is once the input sequence lengths start increasing, the efficiency, power efficiency actually drops significantly, okay? And I don't even plot the ones below 1 because these are too low to be able to, for us to use. So the 80 token thing that I circled here is signifying this is what normal traditional NLP task would use, like Google search would use 80 tokens. That's about what it is. So the current platforms actually provide okay efficiency for that. But as you move to having longer input lengths, and why do we care about that? Vision transformer, state of the art, what it's doing is taking an image and then separating them into 32 by 32 pixel patches in order to feed into the transformer. So that translates to about 1024 input token length, which is what I circled here. So you see, if we want to perform vision transformer inferences on the current platforms, such as TPU and GPU, you're going to get power efficiencies that's so low that it's not going to serve the purpose of doing edge computing. That's why this is important for us to create another accelerator that's hardware-software co-designed with power efficiency. So how did we get this efficiency that I just showed you? So in order to build an accelerator, the first thing we do is we write the workload. So what we do is we take the BERT transformer inference workload, we actually characterize them, and found that actually there are 3 operational sequences or data flows that account for 90% of the inference time. So if we can accelerate these very efficiently, then we can get the power efficiency and the speed up. So these 3, the first one is a matmul followed by a matmul plus a matrix SIMD operation, such as multiply add in this case. And the second data flow is actually the same sequence repeated twice and then followed by a special function. And in this case is a gay loop. The third sequence is actually a matmul followed by a matrix divide, and then a exponential followed by a matmul. So this exponential and the matmul, this part is actually the softmax, okay? So these 3 data flows, they are cross layer from the model. So if we can group them into these 3 data flows and accelerate them, we can actually achieve exceptional efficiency. So another thing to note is that the workload uses different sizes of input matrices. So what we found was if we were to supply with a heterogeneous systolic array, you can get better utilization instead of having a homogeneous ones like the TPU provides. TPU provides 256 by 256 systolic array. And to increase the efficiency, we propose to use some number of M-type large systolic array and some number of G-type medium systolic array and some type of a small E-type. So what these types are is each of the systolic arrays are outfitted with special functions. The E has the exponential. Besides having this heterogeneous systolic array, we also architected them to be output stationary so that intermediate data can be stored in accumulators within each PE. And another thing that's important is because the models are so large, and even with the A100 card that has 80 gigabytes of memory on it, we still run out of memory when we do model training, okay? So what we did was we decided to use streaming systolic arrays that also puts pressure on the communication between the host and the accelerator. So we're basically trading bandwidth for memory storage. Another thing we did was, because we wanted to execute MapMol followed by a matrix add or a matrix divide, we added these SIMD units on the left of these systolic arrays and made them left rotating so that we don't have to go back to the host whenever we want to do this operation specifically. The last thing is we added these lookup tables to approximate special functions such as DALU and expo, and this also allows the data flow to stay on the accelerator itself without having to communicate to the host. So we did design space exploration. Details can be found in the paper. We try to figure out what is the optimum for how many E-types, how many G-types, and how many M-types of systolic arrays. So this is showing a configuration of the most efficient design, which has 20 E-types, 3 G-types, and 2 M-types systolic arrays. And they are orchestrated using a 32-thread host program. That's allowing us to achieve about 80 to 90% utilization on these systolic arrays. Okay, so this is basically the end of my talk, and I'm just showing that with this Burr accelerator I just showed you, it's going to serve as a good basis for us moving on to design the Vision Transformer accelerator for Edge Data Center. And now I'm going to have Abhishek come and talk about how to do system support for accelerators.
Right. Hi, everyone. So I'm Abhishek Bhattacharjee. I'm an associate professor at Yale, and I'm going to be telling you about how I've been working on integrating, programming, and coming up with the system support necessary to use the accelerators, some of which Lisa talked about. So just pictorially, this is where my work slots in against the picture that Lynn presented earlier this morning. And so you can think of my work as taking accelerators that are not just the kinds of vision or transformer accelerators that Lisa was talking about, but GPUs, FPGAs, a whole array of them, and integrating them into the kind of disaggregated systems that Anurag is building to support the types of DNN inference services that Lynn mentioned earlier today. And although I'm in the early stages of figuring out how to integrate these accelerators, I think up the pike we can expect that their integration will also pose interesting fault tolerance, security, and fairness problems that we'll have to address in the upcoming years. Okay, so in more detail, and let me see if I can so in more detail, this is what you see when you zoom in to one of the compute nodes in the disaggregated kind of setup that Anurag has been building for the edge data centers we've been looking at. You'll see that they're powered with CPUs, but also this whole host of various kinds of accelerators. And the key thing here that determines the performance is not just the compute, but also the memory that's integrated with all of these accelerators. Right, so you have high capacity host memory, but it's slow to get to versus the kinds of lower capacity but higher bandwidth memory that your accelerators hook onto. In fact, the host memory itself can be quite slow to get to if you consider the kinds of disaggregated memory systems that Anurag is working on. Right, you might have to go over the network to get to some of that host memory. Really the question is, how do we manage the data that we have that's hot and place it in the most appropriate memory device to maximize our performance and meet the kind of SLO goals that Lynn's inference services have. Now, accelerators, they were designed originally as co-processors to the CPU. So the picture of the world that we had as of, say, 5 years ago even, was that you had to have the programmer manually orchestrate all of the data movement between your high performance and low capacity memories, but your higher capacity and lower performance memories with this. So suppose that you were running one of the kind of image processing workloads that Lynn is interested in. You'd have to figure out how to take the core data structures that were being operated on and manually transform that into data that could be kept on a GPU memory if you decided that the GPU was the right vehicle to actually extract performance from your workload. This would involve copying data. It would also involve, very crucially, transforming new sets of pointers on your address spaces for accelerators. The programmer would have to do this manually. This is difficult, this is not portable, there's a whole bunch of problems with this, which all mean that it's really not the way we want to go when we're thinking of building the disaggregated data centers we have. We want all of that complexity to be hidden away from the programmer. So a lot of my work has been on how can we provide a unified address space for all of the accelerators and CPUs in our system? How can we manage that unified address space with the operating system and runtime layers so that the programmer doesn't have to do it? How can we make it so that a pointer looks exactly the same, whether it's the CPU or GPU or FPGA or whatever else you have? And how do we do all of this memory movement under the hood while achieving good performance? And that's the hard part. So the portfolio of my research over the last 10 years really has focused on this. It's not just what I've been doing for this Athena work. So I've done a lot of work on the operating system and driver stack to enable automated movement of data to get the performance that we need. I've also done some work on hardware support for this. There's been a lot of industry impact from this work. So several shipped, GPUs and CPUs with this work, a couple of billion Linux distributions that have been used. And so the work I'm going to be deep diving now into is based on all of this work and sort of builds on the industry contacts that I have made in the course of addressing this problem. The deep dive I'm going to do is about an upcoming HotOS paper that I've published, along with Anurag, who's also part of our AI Institute, as well as collaborators at NVIDIA. So the work that we've basically been looking at is how do we move memory between our various memory nodes? How do we move pages of memory to maximize performance? In particular, memory prefetching is absolutely vital to all of the operating system and driver stacks that companies like NVIDIA release to hide latencies of getting to data, right? But the prefetching heuristics and mechanisms that are there in state-of-the-art drivers are woefully inadequate to tackle the kinds of dynamic changes and configuration changes you see in the edge data centers that we're interested in. So the right thing to prefetch and the right time to prefetch is dependent on your workloads, their inputs, the phases the workload is running at, what compute engine you're trying to get the data close to, and that compute engine's ability to tolerate latency, what memory allocators are you using, whether you're multi-programming, do you care about tail latency, do you care about average performance? There's many systems dynamics to consider. And that's why, if you look at state-of-the-art work coming out of Meta, Google, that are also trying to tackle similar problems, they're really looking at machine learning as a way to try to handle that vast state space of design configurations and scenarios for which you need to adapt prefetching. Here's the problem with machine learning. Machine learning, to do this effectively, needs to happen online, but online learning is hard. There's overheads associated with it for both the compute and memory side. You need many training examples to make good decisions. And even once you've figured out how to make good decisions for one workload and one phase of its execution, for one input scenario, making very slight changes to that workload's even inputs leads to this phenomenon called catastrophic forgetting, which is really well known in the ML community, where you learn sort of one function, you get new training data, now you have to learn a different function. So what we've been doing is looking at the brain as an inspiration for how we might be able to offer online learning mechanisms that address some of those problems. The brain is a really efficient online learning vehicle. How it tackles all of the scenarios and problems I raised before is by using two separate subsystems to manage. You have a neocortex in the brain that's good at learning complex rules that you need to learn across different tasks. The catch is that it learns those complex rules by looking at many, many training examples. The question is, what does the brain do while the neocortex is forming those complex kind of representations? It has another subsystem called the hippocampus, doing sort of faster learning. It's more like one-shot learning that it's doing. It's doing this with high compression. It's not good at learning complex rules, but it does give you some leeway while the complex rules are being learned. If you actually look at what's called the complementary learning system theory of how the brain does this, there's a lot of details on how the brain uses these two subsystems to learn new activity while replaying or interleaving what it's learned from before, like prior training examples. There's a lot of theory on how the brain does not use backprop and maybe relies on simpler learning mechanisms like Hebbian learning. And we are exploring a whole host of these concepts to see whether we might be able to mitigate the problems that I was discussing before. The long-term target that we have, that we're trying to build towards, is a prefetcher that looks like this. This would be built in software for our initial target. We would be trying to build this in an operating system kernel. In particular, NVIDIA's Unified Virtual Memory Driver is our first target to do this. I don't want to dwell on the various boxes here because there's a lot of sort of neuroscience research that informs this, but certain sort of keywords that should be, you should be flagging. We're trying to learn abstract structure between tasks. We're trying to find fast ways to complete patterns or associations, which is basically what prefetching is. You look at a stream of references and figure out what the future ones are. There's all aspects of compression, pattern separation inspired by how the brain works that we're looking into. But some very quick quantitative results to tell you where we're at. So we first wanted to show you here the impact of that catastrophic forgetting problem that I was talking about before. So this is data collected on the disaggregated system that Anurag has built using memory traces that we've extracted from that. We ran separate workloads that exhibited different kinds of stride behavior in their memory access patterns. So the graph on the top shows you that a network that we picked, it's a Hebbian network with one hidden layer of about 1,000 neurons. We train it to learn the activity of a workload that strides with +1 pages, and then we run we put this network and have it learn the activity of a new workload that's striding with -1. What you basically can see is that as the -1 stride is learned, so that's the blue bar, and the network's ability to learn that, its recall of the red line or what it had learned before drops off. And so the question is, how can we have both of those learning effectively? We don't want one to drop off while the other one picks up. That same phenomenon you'll see in the graphs at the bottom as well for other kinds of memory access patterns. Now, what this set of graphs shows you is our first cut at taking inspiration from how the brain interleaves training data that it's looked at before versus training data that it's seeing now to remember both those patterns. And what you can see on the graph on the left is that using extremely naive forms of replay, which is how the brain does this, you can still remember all the kinds of functions that you were realizing. Now, there's a lot of work we need to do to make this tractable for deployment on a real system. This is just a simulated scenario right now, but that's sort of where we're at and what we're looking at. Some other data that I think is interesting to consider here, the graph on the top shows you how prefetching accuracy fares when you take a Hebbian network that's about 1/3 the size of the state-of-the-art LSTMs that Google has published to do prefetching. Blue bars show you our Hebbian network. The orange bars show you the LSTM. In terms of prefetching accuracy, that is accurately predicting the next target memory page address, we're faring pretty similarly, and so that's good. But what's really good is the graphs at the bottom, which show you the inference time and the training time for the Hebbian network as a function of the number of predictions made. Those are the purple trend lines that you see below, and you'll see that on a log scale, we're significantly faster than what you might do with LSTMs, even if those LSTMs are multi-threaded, heavily quantized, or you throw other kinds of optimizations at them. So what we're doing now is trying to prototype these concepts in, like I said, NVIDIA's GPU driver as an exemplar of how we would integrate this for accelerators beyond GPUs themselves. We're working with NVIDIA engineers to do this because there's a lot of details that we have to work through about the page fault stack and the memory management of accelerators to get this right. That's coming up the pike. And in the future, what I envision happening with this is that we'll be able to extend this same philosophy to hopefully FPGAs as a next step, and then the kinds of transformer hardware accelerators that Lisa is looking at and beyond. So that's what I have. Be happy to take any questions.
Abhishek and Lisa for the deep dive into your collaboration. I think we have time to take some questions for the entire pillar or any specific project. Right. Yes. Right. Right. I think, yes. Okay. The question from Rebecca is how things fit together, because it sounds like the talk we talk about is different components. The question is illustrate how we put things together. That's a very good question. I think on one hand, scholarship is always about find a very narrow, deep problem, take deep dive, solve the hard problem. On the other hand, but like we're trying to do in this pillar, is to have overarching theme, get people to work with. I think we have been thinking hard about how to achieve this. There are right now two methods, complement methods. Number one is we have, like I highlighted at the beginning, we have a working test bed, like Miroslav and I have been building in the past year. So this test bed is basically multiple drones, use computer vision to track targets, to map out the environment. That's a application that's relevant for military, for civil uses. And in this setting, the computer vision is actually served from the edge data center. So it's a test bed, like many of this research idea will be deployed and test evaluated. When they're writing paper, they would be able to use this driving vision as something to talk as and number one. Number two, there's several of us who kind of like we're like some of us are herbivore, some of us are like carnivore, right? I'm kind of the omnivore. So there's several of us who kind of cross the stack, work on both the system, the edge data center and edge devices part. That particular, I myself, I think the Abhishek, the accelerator, also work for edge devices and data center too. Miroslav also, I think Miroslav and both Miroslav and Maria, their work actually will innovate on the algorithm that will be deployed in the edge data centers. So I think there's several us who are kind of the omnivore that cross this boundary of devices and help tie things together. And we kind of form the core of this pillars collaboration, and then we loop in a lot of other members. That's a very good question. I think we try very hard to achieve that goal. Maybe we should move on to next.
So the file is needed support just for this.
I supposed to also admitting folks?
No, I'm admitting.
Um, I'm Miroslav Pajic. I'm a associate professor in EC, and I'm going to be talking about our efforts on using these AI and edge-based AI systems, edge-based systems for AI support in building these autonomous services. How can we build collaborative situational awareness, and how can we build autonomy using the systems that Lynn has. I have to use the mouse. All right. Okay, so pretty much the goal of our pillar is to use this heterogeneous edge-based computation and sensing in order to build this assured, robust, and resilient autonomous services at the edge. So how can we provide this high assurance in systems where we have high levels of uncertainty and we have a potential contested environment where we might have malicious activity. And again, we really are trying to both develop the AI algorithms to improve the systems that are providing support for the execution of the algorithms, as well as to center them on specific applications to be able to evaluate their impact. We are looking at something that Iran mentioned, two different types of applications. One is on this kind of multi-drone search and target tracking, where we have really highly resource-constrained devices because of the levels of computation that you can perform on each of these drones with the very limited battery lifetime, as well as setups where we actually do have quite a lot onboard computation, where we talk about collaborative sensing and decision for connected, automated, or autonomous vehicles that have acronym keeps changing over time. So there's quite a few of challenges that we are trying to address as a part of our efforts to build these assured autonomous services on the edge. So pretty much what we have is in these types of setups, we have asynchronous data sources with different types of modalities. So we have computer vision that is providing the high fidelity images. We have LiDARs that are providing 3D point clouds. We have radar that is additionally providing this kind of 3D representation or having the position and the velocity of the objects. We have plethora of data that is being sent from these multi-agents, and we are trying to figure out how can we build this kind of assured autonomy on the edge. In order to do that, the first thing that we want to do is to be able to build this collaborative situational awareness, meaning that if we have a plethora of agents that are able to sense and to use the capabilities of edge-based servers, how can we build accurate situation? And then how can we use that kind of information about awareness for kind of real-time decision-making, both on the local level of each of these agents, as well as for multi-agent coordination. We really are facing here a plethora of different types of technical challenges that we need to address that will really push some of the systems that Lynn talked about to the limit, as well as motivate the development of different types of AI algorithms to guide them. So we really are talking about heterogeneous platforms, heterogeneous sensing modalities. So how can we put them together? How can we utilize these different types of computational? How can we do that in setups where we need to provide strong security and privacy guarantees, especially if we are dealing with potentially contested environment? And there is this interplay between uncertainty in the environment and the something that might be not the uncertainty, but by malicious interference. How can we do that in setups where we need to have very efficient systems so that we can prolong the battery lifetime of these devices? How can we provide these kind of real-time guarantees? Because especially if we want to provide the close the loop we do need to be able to do this with real-time guarantees. There a way to systematically build this, because effectively what we have is we have these highly distributed systems, multi-agents that are collaborating with privacy and security models in place. So how are we building these types of distributed models and architectures in a way that are allowing us to provide these assurance services at the edge? And the last but not the least is how to ensure that we have robustness and resiliency of these systems in setups that are highly uncertain. So we are talking about highly uncertain scenarios, and also potentially there might be malicious interference. So what I'm going to do in the next, I guess, 10 minutes, I'm going to highlight first off the projects and the PIs that are part of the pillar, and then some of the results that we have. Okay. So we pretty much split the work in the part of this pillar into two different setups, and one is working on the trustworthy collaborative perception and autonomy, and the other one is on the system side. And you will see some of the familiar faces that we already talked about. So what we call more on the algorithm side, we are looking at how can we build this trustworthy perception and autonomy in a collaborative manner. And the first project is consisted of a group of PIs from Michigan, Princeton, and Duke, and we are pretty much looking at building these trustworthy models for integration of camera feeds, 3D point clouds, radars, and wireless sensing. So pretty much what we are trying to do is we really are getting the data from lidars, from camera, from radar, and trying to build this kind of efficient model that are providing high performance guarantees for obtaining perception, object detection, target tracking in this particular specific challenges that we are trying to do when integrating these asynchronous data sources is dealing with the heterogeneity of these particular setups. For some reason, the animations are not showing. The other one is we want to ensure that we have that we are developing these realistic threat models for these particular scenarios, because the autonomy and these autonomous agents need to be operated in potentially highly contested environments. Building these models under very non-realistic threat models will really limit their application in the real world. So what we are trying to do is now, if we don't trust the sensing, if we don't trust some of the computing that is present on the edge, how can we develop these kind of realistic threat models that will allow us then to incorporate them into development of models for perception and autonomy. And we are, in this particular case, we are looking at the impact of physical and cyber attacks on each of these modalities: computer vision, lidar, and radar. Of course, now when we develop these specific threat models, how can we incorporate them into resilient perception on the edge, and we focus on the problems of object detection, classification, tracking in these kind of contested environments. Again, that is a collaboration from Princeton, Michigan, and Duke teams, and again, it's trying to provide this kind of address the issue of security and providing resiliency to both uncertainties in attacks where we try to implement the perception. Most of our models are built under some assumptions about the behavior of the environment. It is really important to be able to quickly detect and identify adversarial activities, and some of the approaches that we are using is out of the distribution detection, which is something that Helen will cover in her talk, and Olga has been working on a lot. And again, we really had to pick only a few of the highlights in this, but there will be quite a few posters addressing these topics. So I would really encourage you to talk to who are actually doing most of the work. And yes, and the last but not the least, looking from the perspective of how are we now doing this combination of centralized on the edge server computation and decentralized data aggregation and fusion. How can we develop a secure federated learning model is the part of the component that is having the collaboration between the Yale team, Leandros, and folks from Duke, and this is something that Neil will cover in a lot more detail as a part of his presentation. And finally, the last but not the least, if we now have this kind of situational awareness, if we know what is going on with some level of uncertainty, and we have some model of the environment, how can we build these policies for real-time decision making and control and adaptation? And the collaboration with Vahid and my group, we've been working on the use of robust adversarial reinforcement learning to build these policies that are maximally robust to changes in the environment as well as to the potentially adversarial behavior. So next, like few minutes, I will focus on some of the research highlights that are part of the projects that we've did. So, on the system side, we are looking at how can we do this optimal split between the computation available at the agent and the computation available at the edge. And here we really critically depend on the work that is being done as a part of Lean's pillar, which is the reason why we, like I know you see the shared faces, pretty much the idea is how can we minimize the processing delay on the edge server, how can we exploit this very resource-constrained platform to run these models, what is the adaptation of the models that need to be done in order to allow for their execution on the platforms that have very specific edge requirements. And of course, how are we building this kind of runtime assurance for security? How are we ensuring that if you have exchange of the messages, whether it's between threads or whether it's between agents, they comply with the execution model, which is something that Mike has been working closely with on building this kind. Now I'm going to focus on projects and highlight some of the contributions. So, in an effort led by Song's group, one of the problems that was looked at in the current setup where we are looking at the existing data sets. In the setup where we are looking at existing data sets, so for example, he's looking at setup is a new scene where we have LiDAR and camera. They started from the model of in the standard setup of multimodal sensor fusion. You would try to directly connect the camera features and connect them to the LiDAR 3D point clouds in order to be able to perform this kind of object detection. They somewhat flipped the coin and started looking at it from the bird's eye view perspective. Pretty much the idea in this particular is that by developing these models from extracting the bird's eye view relevant features, it will really significantly improve both the object detection as well as segmentation problems. In addition to, like I know, winning pretty much any competition on new scenes on or Waymo data sets, the computational improvements were very significant by moving by dealing with delays and offline pre-computation for some of these models. They were able to reduce by 40 times the delay associated with the models, which allow them to actually run it in real time, even on some of the more resource-constrained platforms. Again, this was the setup where we start with the LiDAR point clouds, and we start with camera and try to build this fusion model that will provide high levels of accuracy, both object detection and the other problem that we started looking is what changes if we now don't trust the data. And we looked at from additional perspectives, we look at existing, including this one, sensor fusion algorithms, what are the limitations of them if you look at different threat models that the attacker might compromise. And the first problem that we looked was the physical attacks on camera LiDAR sensor fusion, which was the collaboration between Duke and Michigan folks. And we pretty much showed in this setup, I've covered some of this, like in one of the update meetings, was that if you have the attacker that knows everything about the environment, so it's really an unfair game. Attacker knows everything and the system does not. The attacker is able to perform these physical attacks on the vehicle in a way that they are compliant with what the camera sees, but they are changing, adding additional points in the 3D point cloud that are exploiting the shadow region behind objects in a way that is moving the detected object. Why is that important? It's not important from perspective of whether we detect that something is there or not, but the of this detected object is really then propagated through the rest of the system, meaning tracking, prediction, finally the low-level control are directly impacted by this. And something that we really are trying to connect as a part of the Athena efforts. If you're just interested in object detection, if you're just interested in tracking, you might not need to have 100% because the other modules in the whole autonomy pipeline, the autonomy stack, might be able to iron out some of the errors that are happening. Some of the particular problems will really be amplified through the rest of the autonomy stack, and that's why it's really important to look at this in this kind of holistic view, and why it's important for all of us to tightly work together as we have in the past period. So, in this particular setup, looking at both on the Kitty data set as well as Baidu simulator, we were able to show that you can really launch these types of attacks, that just by moving the vehicles in the scene, fool the rest of the autonomy. So, for example, you can have the car that thinks, oh, this vehicle is moving out, my cruise control can start speeding up. By the time it detects that there is an object there, it cannot stop and it will hit. And as I said, we've shown that these problems both on existing data sets as well on the simulators. I'll keep on mentioning these simulators because that's going to be one of the problems that we've. Then, in the past few months, we looked at what if you don't have these types of setup, where you have the attacker with the physical access. What happens if you now have cyber threat model where the attacker was able to download malware on only a subset of the sensors? Why is that important? Because in that particular setting, the attacker does not have full information. We are looking at these partial information models that can occur. What can the attacker do in that particular setting? And we've shown that it's really easy to launch. We really show that it's really easy to launch both on the data sets as well as on the existing attack. So this is a stealthy attack. This is an attack that is detectable if you only use LiDAR. If you use LiDAR camera attacks, this is an attack that does not know even the position of the LiDAR on the car. It does not even the height. We are running a model that is able to implement this kind of local perception from a single node, and now is able to generate these types of inputs that are fully stealthy. On the one side, in the collaboration with Vahid's group, we have the technical proofs on how to launch these types of attacks that keep the residues that are used for anomaly detection, their distribution the same. On the other hand, as I said, like this, the collaboration with Duke and Michigan teams that were able to show how you can build and evaluate both on real data sets as well as on Baidu Apollo, how you can develop these types of attacks, as well as defense schemes against these attacks that provide high level of guarantees even in the presence of attacks. Now, in the collaboration with MIT, we are trying to look at this both from the defense perspective as well as the attack perspective. These are somewhat larger models to build this kind of perception from the attacker side. How can we significantly reduce them so that we can actually run them on a smaller platform, both from the red team's perspective, but as well as for this kind of additional add-on that can filter out some of the safe models. Literally, one of the examples where we had researchers from schools coming together to develop the suitable threat model as well as suitable defenses for these types. Again, this was from a single vehicle perspective. If you move from a single vehicle to multi-vehicles, a lot of these problems will go away. And this is something that, again, it was led by the group from Michigan, but it was, again, in tight collaboration with the folks from Duke. And Morley's group looked at the problem of collaborative perception. And sure, there are some problems even on the security of collaborative perception. Again, we've both identified the security vulnerabilities in existing collaborative perception models used in autonomous vehicles, but also provided defenses that can significantly reduce the attack success rate in this setup. And we've evaluated this on an MCT test bed where we showed both how to launch these types of attacks as well as how these. Another example of the work that has been done was something that has been led by Vahid in collaboration with Vahid and my team. It's how can you build this causality and how can you build up learning in highly changing scenarios where we are pretty much trying to use transfer learning to quickly adapt to new conditions. The idea is it is really important to understand the impact of proposed actions, and to do that, Vahid's team proposed to use the individual treatment effect in a suitable causality framework. And they were able to show that with doing that, they're able to significantly reduce the amounts of incoming data that can be used to train these models to adapt to even highly changing environments. Just some of the examples of the different types of research efforts that were led by folks from different schools. If we have time, I have a lot of backup slides to cover the other PIs. Time's up. Okay, what I want to use is for the next 2 minutes is just to highlight some of the test beds that we use to guide evaluation and development of this. So we look at two different problems. First one is we really like to play with physical. We like to build physical demos, and it will be awesome if everyone can have full access to everything, to the phones, the cars that we are fortunate to have, both in the multi-agent drone setup as well as with MCT. But there is also the very I don't have to talk to this crowd, the importance of open loop, open source data sets and simulators. However, the problem is, let's say that you are interested in object detection or you're interested in one part of the perception model. If you want to evaluate its impact on the full autonomy stack, you really need to find the implementation of everything else. And let's say that you want to do that on Kitty data set, but now your advisor says you really need to do it on new scenes. Okay? That's awesome, but now you need to manually change everything. And it was a huge problem for us, and especially it's amplified when you have folks from different groups. So to do that, we've spent the last year developing AV-Stack, which is a reconfigurable platform for autonomous vehicles. So for example, if you look at here, just a general high-level implementation of autonomous vehicle stack with perception, localization, tracking, prediction, and planning, you really would love to have this kind of plug-and-play capabilities to say, I want to use this control module, or I want to use this localization module, or these types of perception. What we were able to do is to develop this kind of interface that allows you to use a plethora of open source solutions. One of the things that we will require of everyone in this project is whenever they develop a new algorithm to developing a certain interface that is really allowing us to plug and play with the rest of the system. We can connect new scenes data sets, connect Kitty data sets. We are able to do this with Carla Simulator. So you really want to do closed loop control with open loop data sets, you cannot evaluate autonomy, but with connecting it with Carla, you can really see, hey, this works very well on data sets. It doesn't work so well in closed loop. So we can really change environments and evaluate this. Even if you are one part of our ecosystem, you can evaluate on the full system. One thing. The other thing is, it really is super easy to build these kind of collaborative scenarios. So where you have the information exchange vehicle to infrastructure, vehicle to vehicle, and perception from several drones. And we are able to both incorporate some of the data sets that Morley provided, as well as to build our own that are based directly on Carla. And we have both publicly released these data sets, as well as integrated, for example, the one that came from UCLA as a part of the full. Of course, yes, this is just from Kitty, from New Scenes, and this is from Carla Simulator. Of course, we also have the physical test bed with drones. This is, for example, one of the experiments of running the edge server outside of the building that we will have the meeting yesterday. So here, in particular case, we have 2 drones that are collecting that are taking their videos, and this is test bed. The drones are here. The Edge Data 7 is at Yale, and they are building. The mapping is fully done on the Edge server. Again, for all of these, all of the models that are being developed as a part of Athena, there is this opportunity and really a lot of emphasis on evaluating on these types of both software-based, simulation-based, or physical tests that are allowing us to check how do these things work in real life. And it was fully with the perception perspective. We also have a test bed where we do like indoors, where we are performing control. For example, this is just one of the illustrations. All right, it gets really loud. This is just one of the illustration of a setup where we have 2 drones following targets on the ground. Again, everything is done at Yale, so they are pretty much running. They are sending the data on the edge server using the systems that and the scheduling that Lynn talked about in his talk. We are able to perform this kind of information fusion in real time, send the data back, and you can see how, although one drone is not able to look at not able to sense the target, it is able to get this global situational awareness and keep the track of the drone. So with that, I would like to stop, and I would like to invite Neil. Where's the...
Oh,
yeah.
Okay. Hello, everyone. I'm Neil Gong. I'm assistant professor at Duke University. So our project is about secure federative learning. As Miroslav mentioned, example use cases in collaborative situational awareness include multi-zone search, target tracking, collaborative sensing, and decision making for collected automated vehicles, and so on. These use cases inspire us to study federative learning, especially the foundations of general federative learning. Specifically, in a general setup of federative learning, we are given some clients, which could be drones, automated vehicles, smartphones, and so on. Each client has some data locally and maintains a local model using its local data, and then send the model updates to the server. For example, the server could be an edge server, edge data center. Server maintains a global model by aggregating the model updates from the client. And the global model is trained via multiple communication rounds between the server and the client. After training, the global model is deployed. However, due to its distributed nature, federative learning is fundamentally vulnerable to poisoning attacks. An attacker can have control over some malicious clients, which could be compromised genuine clients or fake clients. These malicious clients can arbitrarily poison their local training data or poison their local models, their model updates sent to the server. And eventually, the global model is poisoned, and the poisoned global model makes incorrect predictions as the attacker desires. So our project aims to secure federative learning against such poisoning attacks. And our methodology follows the general philosophy of prevention, detection, and recovery. Prevention means redesigning the federative learning algorithm to prevent attacks. Detection means we want to detect the malicious client, while recovery means we will recover a clean and accurate global model after detecting malicious clients. So let's briefly go through each of these three directions. For prevention, we propose an ensemble federative learning framework to prevent poisoning attacks. Let's use an example to illustrate our idea. In this example, we have 5 clients, C1, C2, until C5. C5 is malicious and could perform any poisoning attack. Instead of training one global model, we train 3 global models in this example. Each global model is trained using 3 randomly selected clients. And W1 and W2 are trained using benign clients only. However, W3 is trained using clients that include the malicious client C5. So W3 is poisoned and may have arbitrary behavior. Given a testing input X, the global models W1, W2 still make correct predictions, but W3 makes incorrect predictions. However, the majority vote among the 3 global models is still correct. And as we can see, the majority vote prediction is correct, is guaranteed to be correct, no matter what attacks malicious client C5 performs. So our prevention method can actually achieve certified accuracy, which is a lower bound of testing accuracy, no matter what attacks the malicious clients perform. In this graph, the x-axis is the number of malicious clients, the y-axis is the certified accuracy, and this curve corresponds to Fed average, and this curve corresponds to our ensemble Fed average. So as we can see, when just one client becomes malicious, the certified accuracy of Fed average reduces to 0, because one malicious client can arbitrarily change the global model learned by Fed average. However, for our ensemble Fed average, when 20 clients become malicious, we can still guarantee a certified accuracy of at least 0.85. So remember, the certified accuracy is a lower bound of testing accuracy. However, a prevention method can only prevent a small number of malicious clients. For example, in this graph, as you can see, when there are 60 malicious clients, the certified accuracy, which is a lower bound of testing accuracy, reduces to 0. So we also started detecting malicious clients. The key idea of our detection method is as follows. A benign client computes its model updates based on its local training data across multiple training runs. So the model updates from a benign client have some sort of consistency across training runs. However, a malicious client crafts its model updates without using its local training data, all following the algorithm. As a result, the model updates from a malicious client have some sort of inconsistency across multiple training runs. So based on this idea, we designed a method to distinguish between benign clients and malicious clients. This table shows some results. The first column shows different attacks. The second column shows different variants of our detector and a baseline detector. And the third column shows the detection results. So as we can see, although our detector is not perfect, it's pretty accurate. After detecting malicious clients, the global model is often already attacked, is already poisoned. So we need to recover the global model to be a clean and accurate one. And a naive baseline recovery method is to just retrain from scratch, which removes the detected malicious client and trains a global model from scratch. So this method is accurate, but it incurs a large computation and communication cost for the resource-constrained client. The key idea of our recovery method is to retrain a global model using estimated client model updates instead of asking the client to compute their model updates again. So during the original training, the server stores the client model updates. And during recovery, the server uses the stored model updates to estimate client model updates without asking them to compute the model updates again. So in this way, our method can be more efficient. So let's see some recovery results. So when there are no attacks, the learned global model is pretty accurate. But when there are attacks, the learned global model becomes much less accurate. And after we detecting the malicious client, for example, using our previous detection method, we retrain a global model from scratch. Using the remaining clients, the global model becomes accurate again. But the communication computation cost is very large. Our recovery method can recover a global model with similar accuracy, but saves large amount of computation and communication costs for the clients. So to summarize a little bit, our project builds secure federative learning techniques via prevention, detection, and recovery. And for the next steps, we aim to study secure, fully distributed federative learning. So currently, federative learning still requires a central server. In some use cases, for example, multi-zone search, maybe there is no central server available. So those clients may have to communicate among themselves without a central server. That's what we mean by decentralized federative learning. And we will closely work with team members to deploy and evaluate these secure federative learning techniques on collaborative situational awareness use cases. So that's all for my.
Okay. I am Helen Lee from Duke, and I'm going to talk about the situational aware out of distribution or OOD detection. So first of all, let me briefly introduce what is the OOD detection is. And imagine right now we have a classifier. So if this classifier is encounter animal images with a great training performance, and will produce in the expected. However, we are living in an open world, which is very virtualized and dynamic. So what if the classifier is posed to new images or new objects, right? Obviously, the car is magically out of model's knowledge, and of course, we didn't want the model to produce an output of any given classes over here. Instead, what we really want the classifier to tell us, and hey, this is perhaps a novel input, and hey, perhaps this in the model doesn't have confidence in predicting the notified user to double check. So go back to question of what is the OOD detection? Essentially, it is to help us to identify novel or anomalous objectives or informations and use this information for the further processing, learning, continuous learning, and so on and so forth. So with the support of Athena and by collaborating with our team members in the past 2 years also, we explore these topics and by developing fine-grained and hierarchical OOD detection methodologies. We also developing a large-scale unified benchmarking for the community as well. All right, so let me start with the first project on fine-grained OOD detection. So in the figure over here, I illustrated the distribution of the separation of an in distribution versus an out of distribution. The first line is a pretty common setup at early stage of OOD detection. So for example, people use these nitro images as an ID data, and then the numerical digits and use as an OOD data. And the developed methodologies and to distinguish the two sets. In fact, in real world, such kind of a separation may not happen. I mean, it exists, but perhaps not our major target. What is our major target? More like what we call the fine-grained OOD detection. So previously, we have a classifier developed with a set of bird species. And then in reality, it's going to be exposed to more bird species. It will be good for this classifier to identify there is a new bird species and then taking those information. So consider this in real world setup, and we developed 4 fine-grained environments with the nitro imageries, namely aircraft, car, butterfly, and the birds. And if you looking at the previous methodology, in fact, they all perform very good in course and setup. If you're looking at the y-axis here, the accuracy is starting from and close to 100%. However, when we switch to fine-grained granularity setup, they all perform pretty poorly. The y-axis actually starts. And this motivated our work, like how can we handle the OOD detection in the real world and handle the fine-grained granularity situation. So why we start with this works, and we start with an understanding how classifier works. For example, the first figure here shows the sample distributions in space. So different classes and samples and relatively separated and clustered by itself, right? Well, what is the difference of coarse-grained OOD samples and versus fine-grained? Obviously, the coarse-grained OODs is more kind of a dense and clustered, while the fine-grained OOD samples can be close to many or even every ID clusters. So previously, there have been outlier methodologies, but as you can see, these outlier samples is still kind of pretty close to each other and couldn't cover the entire feature space. And then we proposed our methodology, the outlier exposure. What we do is we tend to create virtual fine-grained outlier data by mixing ID data versus coarse-grained outlier. Well, why we are doing this, and we apply software interpreted and target to control the prediction confidence. In other words, our methodology is in trying to regularize the model such that its prediction confident indicate why the data translate from ID to OOD. Okay. Well, a quick demonstration of our results. Again, across in 4 different scenarios in aircraft and butterfly, car versus a bird, our methodologies and consistently improve the fine-grained OOD detection between and at least to 4 to 12 absolute increase in detection. Similar important, it's performed on par with the SOTA method. One, it applies to the coarse OOD data. Well, why we are doing this? Actually, you may notice this, and here is the OOD detectors, telling us and the classes of giving animal classifiers, and it's also telling us and possibly the input they do not know. Okay, so what we call this an OOD detector is a binary output. Essentially, it says an yes or no to the user. Well, such a binary information is very limited. It couldn't provide a lot of kind of useful debugging information. Basically, we say it's lacks of. Well, also, if we go back to the real world setups and when we're talking about ID versus OODs, right, the definition of the OODs could be very different. For example, when we're talking about the bird species, another bird species can be taken as OOD of the ID data. Well, of course, in such a digit OOD of the birds and classifiers. Well, but clearly, it has a very different semantic information to our classifier. More than this, and with kind of in such setups, and it's very hard to scale to a large number of the training classes. On the other hand, and from our knowledge and in AI communities, and we learned that hierarchical classification the class and structure. So we propose this in hierarchical OODs and see whether we can improve this interpretability. Well, our methodology is also quite. We developed a hierarchical classifier, in which every node is in softmax conditioned by its parent node. So basically, every node will produce a probability. We also can define the path probability, which is the product of the probability of nodes on the path and the route back to the beginning of the inputs. While we have this information, and we can also apply the threading methodologies. The threading, again, can be applied to the nodes or the entire path. So essentially, with the trainings, and we can calibrate it and the made model itself or the OOD detector itself, and more or less conservative in this. All right. So again, here is some very rough results. On the left-hand side, we showed ImageNet 100 micro ROC curves and for ID data. Well, the very dark blue curve then shows the data for IDs, and they all performed really good. And when we blend more OOD data and performance and degrade it, well, interesting observation is, and when we apply the path and probability thresholdings, it can recover the performance. And the right-hand side and represent the hierarchical distance while we are applying thresholding predicts, and essentially our methodologies, and also improved ID and the OOD performance and simulation. So in the past few months, and actually our group has been working on developing open OOD, which is a comprehensive and benchmarking for OOD detection. It's a very giant and chaotic map and show basically we try to summarize and the research progress in the past in the community. Well, over here, each box represent the experimental setup of one research paper. And within the box, and there are many small colorful boxes, and each color box and represent the data used for ID or the OOD setups. So roughly, when we're looking at this, and you can see that the experimental setup for the OOD detections and actually is very inconsistent. There's no standard ways to do the evaluation at all. In fact, in our experimental setups and also evaluation shows that because of the kind of a very random arbitrary setups and of prior works, and they usually produce some counterproductive and understandings, and which is not healthy to the community. So we've been working on this in benchmarking. So exactly what we do is we implemented 40 SOTA methodologies, and within uniform the frameworks we developed. Then we carefully developed the realistic and fair ID versus OOD splits in these setups. And then we performed comprehensive evaluation on all these methodologies, for all these methodologies on standard data sets, including CIFAR and ImageNet. So there are some interesting takeaways, and for example, OOD detections on very large data set is still very, very challenging. We also find that when we can apply mean-time regularization and post hoc inference technologies and to boost the performance. So this is an ongoing work. We target to submit it to NeurIPS this year. So as you can see, I've been talking about several methodology and also the benchmark we have been developed. What is the next step? Our next step actually is to concrete this in benchmarking and then apply this in techniques into real scenarios. It's not only about image classifying, but also we can apply to more complicated tasks like objective segmentation as well. So, for example, when we're talking about the fine-grained versus coarse-grained OOD detections in real world and setup like autonomous cars and environment detections, the fine-grained information could be useful. Like we wanted to get finer understanding on what types of cars, maybe animals will be detected. Well, the hierarchical information can help us to determine some of the branch, some of the information that we a little bit rough understanding, but the others we can have a more finer understanding. So I mentioned about maybe new types of cars and important for the classifier or objective detection. Well, do we have to distinguish different types of traits? Maybe not, right? So our hierarchical OODs can provide such a flexible. And of course, the benchmarking is important because this can help us to evaluate effectiveness of different OOD methodologies and identify the ones for the given scenario. And we can apply that to our application domain. Yes, and this is to conclude my summary of our research. So very importantly, at the bottom, we're going to release an open OOD in 2 weeks also by submitting the NeurIPS paper.
Thank you, Helen. So we will take a short 5-minute break now, and then we'll join back to do the collaborative XR pillar presentations. 2 quick announcements. Pick up your attendee gifts and t-shirts, beautiful Athena t-shirts, front desk. And students, you may start setting up your posters anytime between now and noon, and there are volunteers outside waiting to help.
For sure, Councilman. So each year we pick out the color corresponding to the participated institutions. Last year was blue for our T-shirt. You can guess this year, so this color belongs to which university? Okay.
Okay, thank you. Pausing for a short break. Hi. Yep, got it.
Because I
There is no camera. I knew that.
don't make this, just give it screen sharing, then waiting message. To remove this from being a host,
Oh,
but
okay.
instead go to security and say screen share.
Okay.
Good morning. I'm Shuman Banerjee. I'm the pillar lead for the Collaborative XR pillar. And before I get into this, I thought I should start with a question. Lynn very eloquently talked about large language models and the relevance of that in the broader context. So I thought I'll pose a more simpler question asking, why do you think, if my cursor works, why did ChatGPT get into edge computing? Think about that a little bit. So actually, I asked ChatGPT this, okay? And exactly, I asked this question, and this was the answer, because it got tired of being stuck in the cloud all day. But actually, even though it sounds a little funny, I was thinking about this. I was trying to actually interact with ChatGPT and find some jokes to start the talk with. But it's interesting about thinking about how to bring large language models to smaller, simpler devices. And I think that's actually a path that this institute is going to embrace and be something that's kind of going to be very important in the future. So with that, I will give you a disclaimer that after these slides, no other slides were generated using ChatGPT. These are all our original work. Okay, so on to Collaborative XR. So let me first set the stage. I know some of you probably know exactly what Collaborative XR means, but I just want to set the stage of what Collaborative XR really is in the context of this pillar. And I think what we tried to do in this pillar is try and identify very specific applications that will help us ground our activities in reality, right? So whenever we have to make assumptions, we will think, okay, this is the exact problem, and that's why we will be doing this particular path, or we'll take this particular assumption. We'll talk about the team, but let's start by taking the two example applications we have in mind. The first is use of augmented reality in public safety. Okay? So we all know public safety can be a very stressful job. People involved make split-second decisions under very stressful conditions. And one example which we have been working with through collaborations with local public safety folks in Wisconsin is, say, imagine firefighters going into a building, and they have to do tasks like indoor navigation. They have to collaborate between different people. They have to coordinate their activities. And some of these are very hard even in normal circumstances. They have to do it in an emergency, so this is challenging. And the goal is to use
augmented reality or extended reality headsets to enable real-time, high fidelity and high reliability operations. Okay? So these are some of the tasks that we want to enable, and we want to enable better using AI techniques, using edge support, and using collaboration across multiple devices. So to give you examples in this overall system, you have these end devices, which are these headsets, the collaborating headsets. You have the edge data center, which is hopefully within some low latency proximity of the end devices. And you will be getting all kinds of data coming from the headsets, which could be LiDAR, audio, images, videos, and so on. There will be computing running on the headsets. There will be computing running on the edge data centers, various kinds of models. Some of them may be split. And then there is, of course, the cloud backend, which can be used for greater coordination. And some of the critical things that we have to deal with in this setting is heterogeneity of devices. We have to deal with real-time requirements, which is very, very important because many times if you are utilizing a headset and you change you move your head and things don't move with your change in vision appropriately, it can actually make you nauseous. So it's very important to meet some tight real-time requirements. And then a very important requirement is energy efficiency. Headsets obviously have to be lightweight. You can't put a huge battery on your headset. And if you want to run high-end computation on your headset, they will actually dissipate a lot of heat, and this can be very uncomfortable. It's not a very practical thing if this thing is getting hot and you're not able to use it for a long time. So we will be, in this setting, some of the tasks we have in this public safety scenario are things like real-time indoor mapping. So people go into a building, this is an unknown space. As they look around, as they detect objects, as they detect walls and spaces, they will be observing some part of the environment. Different individuals will be doing the same thing, and we want to be able to aggregate all that and be able to reconstruct a 3D floor plan, a 3D space, which can then be utilized for future folks who are going into the same space. You can also imagine scenarios where once you have a 3D floor plan generated, somebody outside, maybe the commander of this operation, wears a VR headset and does a walkthrough to get a sense of what's going on. So there are lots of interesting opportunities that this setting provides us with. We also want to do things like provide navigational cues. So imagine somebody's gone into a building, somebody else wants to follow that person, and there are breadcrumbs left around the space that allows you to go and reach and trace the path of somebody ahead of you. And it allows you to avoid unsafe areas because somebody has already figured it out for you. You can also potentially leave cues in the space, virtual cues that point you to different objects of interest in this physical environment. So that's sort of one set of activities. So you can imagine there is this end-to-end pipeline where sensor data is generated. We'll be creating various kinds of surface meshes to understand the 3D and 2D spaces. We'll extract and then render it. We'll construct the entire end-to-end system from assembling data from multiple collaborating headsets. And then we will also have this vision pipeline where we are doing object detection and learning and trying to figure out how the environment looks like and provide people with various kinds of guidance. Okay? This is one example. We have segmented different activities within this broad space that are being led by different parts of the Athena team. So we have continuous localization and mapping, which is an important part of generating these 3D maps and helping with navigation. We have object detection and learning, which is critical in any of these environments to know what is appropriate for various interactions and what is not. Energy efficiency is a critical pillar, a component of this pillar because of the factors I mentioned. There is a lot of data that has to be processed, and being able to efficiently compress it so that it can still be used by the application is very critical. So you can, of course, imagine different kinds of lossy and as well as lossless compressions. Lossless is nice, but not always efficient or in terms of compressibility. So if you go to lossy compression, I think the big challenge is making sure the data is still useful and you don't lose important bits out of it. So tying it to the application requirements is important. And then there is need for federated learning because you might be building different models and different headsets, and you might want to create combined models which still help you keep certain data private in different devices. All of these are interconnected. Decisions in one impact the other, and you can easily see some of these relationships in this activity. Finally, there is also user interactions. There is interfaces that we have to design that make activities in this space simpler and more efficient. So the other scenario that we have in mind, again, they are somewhat similar, but they have some fine-grained nuances, and we want to keep both of these in sort of context. These are both challenging environments, challenging designs to get right. So we wanted to consider both of them in our overall project. So the other one is use of virtual reality in educational settings, and the scenario that we have in mind is a classroom of students do a virtual field trip, right? You go to a virtual tour of a museum, a natural history museum, and different individuals are standing in different locations, and they're looking at the same object from different places, and they want to have the shared experience of physically being in a museum, but of course they are virtual. So you can imagine that there is a lot of content that are going to be streamed to these headsets and being combined in interesting ways. You have to understand the perspectives of different users. So there's a lot of computing and management of data that has to pervade across these different devices, which are limited in capabilities. And with edge support, you can do something very interesting in this setup. So again, some of the same tasks come in. Maybe the localization task is a little less relevant here, although you still need to localize users in the physical space, but not to the level you need in an AR environment that you have in the previous setup. So we have different groups focusing on these different pieces. So let me talk about some of the activities that has been going on. I will just preview a few of these very briefly, highlighting more work of people who will not get to speak here today. And then I will invite a couple of our pillar members to talk about their pieces a lot more in depth than I'll get to present here today. So in the object detection and learning, we have Maria, we have Helen, Morley, and Song, who are all working on different parts of it. Broadly, we are trying to deal with large models. We want to handle diversity of objects, especially in unknown environments. And we've been looking at techniques that allow for model compression, which is very important to be able to run it on headsets. We're looking at split models because you can't do everything on a single compute point. You have to split it across, say, the edge and the end device. And then, as Helen spoke about, there is the need for open set detection techniques. This is actually, she spent a lot of time explaining that in the previous talk, but it's an important part in, say, the AR scenario where you go in, you are trying to detect different objects, but you suddenly observe something and it gets misclassified. It will be a problem. So one of the approaches she talked about is this tunable hybrid proposed networks, where you combine the benefits of classification-based objectness and localization-based objectness. So she has some very interesting results, some of which she alluded to in her talk already. In the continuous localization and mapping, one of the very critical requirements there is to get very precise location data for individuals, because what can happen is if your location performance is poor, it can lead to gross artifacts in AR environments. So for example, you may want to place some marker
Hey,
of some
Sharon,
kind
how
or
are
content.
you?
Yeah, I'm very busy working on summer salary.
I am sorry. I just wanted to let you know
I think somebody who
that
has their microphone on, if you could
this
mute
issue has been resolved.
Oh, it has?
Thank you.
Yeah, I mean, what I did is that we got a tuition waiver from the department here. And hold on, Miroslav is on the phone. Hold on. Hey, Miroslav, how are you?
Great. So we have some pretty good results on how much we can compress, and also input in terms of computational complexity. It balances based on the available computing capabilities of the system. This is some work we are still working on, but I think there are some very promising results on being able to use them in, say, small devices and in edge data centers. Moving on to another aspect of energy efficiency. So compression also helps in efficiency when you have to ship data across locations, but your computational costs also contribute to energy costs. But the other place where it becomes very relevant is if you go to the VR example, there is a need to be able to distribute data to multiple devices, and you cannot always distribute high resolution content to every device at high fidelity. So this is work that Morley has been looking at, which is use of this class of techniques called super resolution, which allows you to, number one, distribute data at lower resolution, but allow the devices themselves to recover the high resolution data using various collaborative techniques. So this requires collaboration across multiple devices, and it reduces the overheads of both computation and communication in this overall system. And the results actually have shown that the average QoE of end users, so imagine this classroom setting where people are looking at this content which are coming from maybe a single source, too many users, but each user is looking at different parts of the scene. The overall QoE of this system is much higher using this technique that Morley has developed, Morley and her students have developed, I should say, called OASIS, which is done very well in multi-device settings in this. Then another aspect of edge computing work that's been going on is work that Young-Hoon Kim is doing at Wisconsin, where he's looking at reducing the XR workload when you're shipping content from devices to the edge data centers. Again, there are many tools in the toolbox that we can use, but basically he's been trying to figure out how to alter the frame rate and frame resolution when you're transporting data from the end devices to the edge. This has direct impact on energy costs, and it has direct impact on overall performance and end user experience. So this has some good results, again, has been demonstrated. There is a paper that he's working on, which shows that the total efficiency in terms of end user experience can be nicely traded off with the available capacity and resources in the network and the computational side of the device. Finally, on the federated learning side, Leandros Tsatsilos has been working on improving the efficiency of federated learning on edge devices. This is, again, for building distributed models on multiple users sharing the same physical space. And the approach he's been taking is to do a two-stage model pruning to improve training and inferencing performance. So in the initial stage, they try to select a single client to prune the model size down. Of course, this will not lead to an optimal performance. And in subsequent stages, they involve multiple clients to fine-tune this process and adaptively discover the optimal model that needs to be identified. And again, in terms of performance, again, they have evaluated this nicely and have shown that it has good accuracy while reducing the number of parameters that are needed to be explored. So with that, keeping this overall picture in mind, all of these pieces are different components of our extended reality system, with collaboration being a key piece between multiple devices and the edge. Today, we will get into greater depth on a few of these topics. I will first call upon Maria Gorlatova from Duke to talk about her continuous localization and mapping work, and that will be followed by a postdoc from Professor Songhan's group, who will talk about something that connects energy efficiency with the use of object detection and learning techniques.
Hello, everyone. As introduced by someone, I am Maria Gorlatova. I'm an assistant professor here at Duke. And I'll be talking about our work on
localization and mapping that really touches upon several other elements as well, such as object detection and energy efficiency among them. Donkey. So let's introduce the stage as to why we are even looking at simultaneous localization and mapping, or SLAM. And it is the absolutely foundational capability for specifically augmented reality. Augmented reality is about merging physical world with digital content. To be able to do that, you have to have a very precise understanding of the physical world. Here's where virtual and augmented reality differ dramatically. That augmented reality truly is about merging physical and virtual. To be able to do that in a mobile device, you have to have an extremely precise understanding of where your mobile device is. So if you are familiar with other work on localization, let's say Wi-Fi-based localization or GPS-based localization, and you are used to localizing your devices, let's say down to a meter in XY space, we talk about something completely different here. We talk about localization at the sub-centimeter level and a localization at the 6th degree of freedom. So we want to know the XYZ coordinates and all the angles at all times. We need to know them very well. The thing is, if you make slight miscalculations about the position of your device in space, what that means is that the virtual content that you have placed will look extremely weird. It will drift, it will shift, it will disappear and reappear on you. It will be produced at the wrong scale, as is shown on the screen here. And then imagine, as someone mentioned, there are in search and rescue applications, this essentially means that your arrow that is supposed to be pointing one way will be pointing another way entirely. It also means that your users will be, the experience of users will be very poor. Your AR device will distract them rather than actually help them. So it's an extremely important problem, and my group has done a lot of work on characterizing it, looking at it across different platforms, building tools that allow us to study it, and ultimately understanding this effect on the users, that AR is a user-facing technology. And if your users are dealing with virtual content that shifts and drifts, it's just a very bad experience altogether. And this is where we can really, as Athena, as Edge AI effort, we can really help this. The state of the art for localization in augmented reality is the so-called visual inertial SLAM. This is where you take visual inputs from your camera, you extract certain features from them, and then you extract keyframes that track those features across multiple views of your device. Inertial measurements are used to help stabilize those inputs, to provide additional inputs for the calculations. And this visual inertial SLAM, there are different variants of it, but it is the standard for localization and mapping for AR. You don't know what the companies do try to keep their specifics of their algorithms proprietary, but there are many open source solutions, and all of this is based on the same VI-SLAM principles. The issue with VI-SLAM is that it is very complex, complex and resource intensive. We talk about processing visual data that is coming at a streaming rate. We talk about computational pipelines that have many different elements, that have optimization within them, that extract different features and try to match them in specific ways. So an example of complex processing for a state-of-the-art ORB-SLAM 3 framework is shown on the screen here, for instance. In addition to being complex, it is resource intensive. So this is where optimizations are needed to enable running this on low-end device as well. You would expect it to be quite good by now, but it really isn't. Modern SLAMs make lots of mistakes, and they don't work very well in dynamic environments. All modern SLAM variants presuppose that the environment is static. So if there are moving objects in the environment, then the features that get tracked across different frames are just incorrect, and that severely affects the performance of the algorithms. One interesting gap in this space as well is that there truly are no online metrics right now that allow us to judge the performance of a SLAM algorithm. SLAM algorithm is an estimator. So to be able to understand how well it's working, you ideally want the ground truth, but you're not going to get the ground truth. So there are no real online metrics that allow you to it's working well and to be able to deploy other resources if it isn't. This is where opportunities for edge intelligence truly are endless. What my group has been working on is, first and foremost, we are pipelines that allow us to separate the parts of VI SLAM that run on device and that run on the edge servers. And slightly non-trivial since SLAM pipelines are extremely convoluted and have multiple dependencies. We're also developing techniques that allow us to optimize how SLAM operates on device and on the cloud, depending on resource availability. So different approaches to the maps that we keep on device, depending on compute and network resource availabilities, and different approaches to what we transmit between device and the edge. So this platform right now, it's working. It's operating with state-of-the-art SLAM platforms. We have the code for it available on GitHub, and my student is going to be doing a demo of this system as part of the poster and demo session here. Where we're getting right now is the point where we have built a framework that allows us to reduce resources spent by mobile devices, since we are allowing moving some parts of the workload from the mobile device to the edge. But this is also where there are some natural points with combining this work with the work of other PIs. So now that we are able to execute different things on local devices and the edge, this is where we can start measuring and optimizing some elements of energy consumption, for instance. There are very interesting opportunities for integrating SLAM, and specifically this type of SLAM. Some of the work on object detection, such as Helen's work and the work that will be presented following mine. As I mentioned, one of the challenges of modern SLAM frameworks is that they do not work well with dynamic objects. And one approach to it is to detect which objects are dynamic. So detect that there are people in your view, for instance, or cars, and extract those objects from the mapping process. So we've built a prototype that does this, but would like to do it better, and this is where better edge-based object detectors would really help. So in addition to this work on platform development and building platforms to be extendable so that we can generalize them to multiple users, so that we can combine them with the modules that are developed by other PIs. We have also been working on this element of optimizing the performance of our systems. And this is where we are deciding on what information our system should keep and what information it should discard based on measures of quality of SLAM estimates. But the approach that we are using right now and the approach that we are showcasing today is based on uncertainty quantification of the map that is built by the devices. So the map that is kept locally and the map that is kept globally, they are approximations. They have certain inexactness to them. And this inexactness can be characterization of this inexactness can be used to derive the best map. So the use of uncertainty quantification here is not new. What is new in our work is that we have developed methods that allow it to work online and that allow it to execute on low-end devices. So effectively, we have created a set of online metrics for mapping quality estimates that enable us to now optimize maps. And we have demonstrated that this outperforms existing techniques that are not based on advanced online QS metrics like ours, that this method dramatically outperforms simple heuristics. in computationally constrained systems and in communicationally constrained systems as well. And so what my student is going to try to showcase in the demo session is a live demonstration of our system outperforming a baseline on your trajectory that you will generate. So it's been working well in our trials, but please stop by the demo, see if it works for you. See if you see how our system outperforms the baseline. But on top of just solving this exact problem of building better maps, the bigger story that we're getting to here is that SLAM requires online QoS metrics that simply do not exist. This is one effort to develop that. We have also a more ambitious effort on trying to actually predict the error that a SLAM algorithm will experience in a certain set of conditions. Let's say us as humans, we actually kind of know if we look at an environment, we can more or less guess, using our intuition, using our knowledge of SLAM, and using our experience. We can guess that in this environment, the virtual content will not perform, will not be stable, for instance. But there's no way of quantifying this and no way of bringing mobile systems capacity into that. That's what we're working on right now. We are working on figuring out how to apply cutting-edge ML that is being developed as part of this effort and as part of other efforts to being able to predict whether the estimate will work under a certain set of conditions. And to be able to do that, we are taking inputs from the camera and IMUs directly. We also take some of the internal parameters of the SLAM modules, some of the data that's generated by different parts of the SLAM pipeline, and we are feeding it into a classifier that is able to tell us whether this environment is or is not good. This is ongoing work. We are refining the classifier. We keep improving the training process as well as the models that we're using. Eventually, I would think that it will require all sorts of advanced techniques to work well in practical settings, but the early results are very good and encouraging. For instance, what you see on the screen there are examples of visualizations of our system's take on the quality of certain conditions showcased in AR. So what you see on top are examples of where our system judges an environment to be good, shown in green, or bad, shown in red. And what you see on the bottom is an example of a trajectory that's colored according to whether we expect SLAM estimate to be good or bad in a certain part of it. And this trajectory is, you can see it visualized in AR, actually. So if we were to do this experiment here, you could see the trajectory displayed here. Someone is telling me that I'm out of time, and my students are showcasing the work in 3 demos. I'm happy to talk more about all of it.
So hello everyone, I'm Wei Cheng Wang from Professor Song Han's lab at MIT. So sorry that Professor Song Han cannot make it today in person. So I will represent him to introduce how we should enable TinyML in XR headsets to achieve like energy efficiency. So first of all, let me introduce for a conventional way. In a conventional headset, we usually have to use an external compute backpack to enable this kind of powerful computing method, because it can provide us with enhanced computational resources, including processing power and memory. But however, it will also have some drawbacks, including it should be infeasible for everyday use. Not to mention that it should be impractical for our emergency use case, because we don't want in our emergency case, when we want to save people's lives, I think we don't want to carry this kind of heavy or redundant backpack, right? So what we want to do should be a standalone headset without any backpacks, because it can provide us with more convenient and user-friendly design. However, it also has some numerous drawbacks, including restricted computational resources, and also with limited power consumption and maybe more heat generation. And more than that, it will make us more difficult to enable real-time processing. And also, under most of the use cases, maybe we will have limited or even no network connectivity. So this all motivates us to enable TinyML, which can offer a promising solution to address all the aforementioned problems. And in the meantime, provide us with enhancing performance and usability on this kind of standalone XR headsets. So what is TinyML or Tiny Machine Learning? TinyML refers to the deployment of machine learning models on resource-constrained devices, and it always used with only limited computational power, memory, and energy. And combining TinyML with XR headsets for detection has like benefits. The first one is we can enable on-device real-time recognition because it will we don't need any like cloud or bulky hardware. And for the second one, we can enable enhanced performance and user experience. Because we can because of the reduced latency, power consumption, and also memory usage. So, however, we found that enable TinyML for object detection or person detection in XR headsets is not as straightforward because there are primarily two reasons. So for the first reason is that its peak memory usage of deep learning models is extremely unbalanced. So as you can see on the left-hand side figure, x-axis here denotes the block index or layer index in a mobile NAV2 network architecture. And the y-axis here denotes the memory usage in megabytes. And you can see that for the first 5 layers, its peak memory usage is very, very large, for like up to 11 megabytes. But for the later layers, it will use much smaller memory usage, by about like 8 times smaller compared to the front layers. And this will make us like difficult to enable TinyML for detection because like when we use HoloLens 2, which is a popular XR headsets nowadays, its level 3 cache size is only about 2 megabytes, which is much smaller than our peak memory, which is 11 megabytes. So this is a big problem. However, some people might like argue that we can directly shrink the input resolution to solve this kind of problem. However, we also found that object detection or person detection applications are sensitive to input resolution. So as shown in this right-hand side figure, with the reduction of image resolution from right to left, we can see that the dark blue curve here, which represents the accuracy of object detection tests. And its accuracy drops dramatically to here. So it means that naively shrinking the input resolution might not be the practical solution for us. So we then start to think, how should we enable TinyML in XR headsets for this kind of detection test? So we then found that one of our previous proposed work, which is called MCUNet-V2, might be a possible and promising way to resolve these problems. So MCUNet-V2 is a method we proposed previously to enable TinyML in microcontrollers. And we then now think, how should we combine the concept or even techniques in MCUNet-V2 with XR headsets? So in the following slides, let me introduce like some of the concepts and techniques in our MCUNet-V2 and how should they combine with XR headsets. So the first technique we want to introduce is our patch-based inference, which can help us break memory bottleneck. So here is the practical 2 convolutional layer example. On the left-hand side, this is the conventional per layer computation. And on the right-hand side is our proposed per patch computation. And for example, the first one, this one should be an input image, and with 2 consecutive following with 2 consecutive convolutional layers like conv1 and conv2, and also their corresponding feature maps. And as you can see, in a conventional way, we have to put all of the 2 feature maps into our memory, which will lead to our lot of memory usage, as I show you in the previous slides. However, when we use our per patch computation, we partition the feature maps into different small patches, and in each run, we only process and also store one of one of the patches into memory. So for example, in this round, we only store this dark blue one, this patch, and also these feature maps into memory, so as to reduce the memory usage. So the results can be shown here. So for example, the blue one represents the conventional way, which is the per layer inference method. And our proposed method is per patch inference, which is denoted in yellow color. And as you can see, the peak memory usage can be reduced by, largely reduced by about like 8 to 9 times smaller than the original one to this yellow one. So it helps us enable TinyML in microcontrollers under only 256 kilobytes of memory. But please note that although we use microcontroller as an example here, we can also adopt this exact same method and also exact same concept on XR headsets. And although patch-based inference seems like very good with decent performance, it also has some like disadvantages. It will incur some additional computational overhead because of overlapping. So this is the exact same example as I showed you in the previous slides. This is an input image and with 2 convolutional layers and also their feature map. So now if we use a 2x2 patch as this yellow one or this another patch, this blue one, and these 2 patches, when you trace back to the front layer, it will its receptive field will grow bigger and bigger. So for example, this receptive field grows to 7 by 7, and thus it will incur this kind of like overlapping area. And this is what we call additional or redundant computational overhead. So we then propose another method called network redistribution to solve this method. Specifically, we reduce the receptive field in the front layers, while we increase the receptive field in the later layers. So by this means, we can like reduce the number of computation from originally patch-based inference will increase 10% of the computation, and with this network redistribution method, we can further decrease the number of computation to similar to the original one. Okay, so because I think I'm running out of time, so let me show you some like results of our method. So for our method, it should be robust and not only fast, but also robust and reliable for both object and face detection results. So as shown in this figure, we can enable like largely improved accuracy of object detection by about like 70% with only limited like more than 320 kilobytes of memory. And on the right-hand side, you can see that this column denotes an alternative method proposed by other researchers called RNN pool. And on the right-hand side is our proposed method. We can see that our proposed method can correctly detect all of the faces, while another method cannot. And we want to emphasize that these are very important because in XR headsets, especially in our emergency use case, because we have to save people's lives, right? So it is very important to enable not only fast, but also robust, reliable, and correct results. And I believe our MCUNet V2 and TinyML is able to provide this feature. And here are some results of our person detection and face detection results on microcontrollers. And as we can enable this on microcontrollers, we believe we can also like enable this, achieve this on a more powerful. So for our next step, I think by applying MCUNet V2 concepts and techniques in XR headsets, for example, like patch-based inference and network redistribution with limited or minimal modifications, including we have to search another neural network architecture or adapt to different system environments, we can successfully enable TinyML for XR headsets because we can enable like real-time processing, reduce latency, memory footprint, and energy consumption, and also decrease hardware requirements. So that's all contents from my side, and I'll invite Professor Suman to introduce our platform for evaluation and deployment. Thank you.
So to wrap up, I want to touch a little bit on platforms for evaluation and deployment. I think this is an important part to bring all these pieces together into working systems. So actually one of the very interesting ideas, and this comes from Maria's group, is to figure out how, this is a kind of has a lot of moving parts and a lot of different components and dynamic environments, and testing, evaluating is very hard. So to bring in some consistency and controllability, I think Mario's team is working on this very interesting idea that we want a controlled environment on which we can do testing, on which we have perfect ground truth, on which we have no inconsistencies when we are collecting data, so we can then do repeatable experiments. And the idea is to use basically game engine-based environments where it's a virtual environment, but you can pretend it's real, and then you can, you know exactly everything, how it's laid out because you created it, and then you can run experiments inside it to emulate all the activities we are trying to do. So that's a very exciting piece of work. We hope to be able to leverage that to bring all components together in a controlled setting. But that is, of course, not the end goal. The end goal is to be moving into realistic testbed environments. So we have been working on building this in Wisconsin, but this is, of course, portable. You'll see some little demos of pieces of this where we are actually working with public safety agencies to also try and understand what real constraints exist in deploying these systems. And we want to be able to evaluate them not only from the sort of low-level systems metrics like energy efficiency, reliability, and all that, but eventually the aspiration is to get to end-user metrics of how much does it help in improving triage time or improving the time taken by first responders. So I think that's actually the final end goal, and that's what we aspire to get towards. But I think we are getting, by the way, we meet as a group every month, and we have, of course, other ad hoc meetings across different PIs part of this pillar. And it's actually quite an exciting journey because we are working with Maria to get her part integrated into our end-to-end system, Song's contributing some of the TinyML pieces and making it work in the headset. So we are trying to bring in different pieces over time. We will hope to have a very nice integrated event here. With that, thank you. I don't know if there is time for questions. End of our pillar.
Right, everyone, it's me again. So at the end of after all these pillar representations, and let me give a very brief summary of our efforts and from AI Foundation perspective. Okay. So at the beginning, the Athena Center developed. We identify 4 task forces for AI research, including enabling the intelligence, having federal learnings for edge computing, improve efficiency of computing systems across all the levels and from edge device to edge data center and the cloud. And of course, security and assurance are necessary components. And well, just now, Lynn, Shuman, and Miroslav presented the 3 use pillars, and we are working on within the center. And as you can see, AI methodologies have been applied to these pillars, and it's also demonstrated significant improvement in the given environment. I think more than this, with the entire team collaborations, considering the real test bed and scenarios, and help us deepen the understanding on this in AI methodologies. It's enable us to know more about what kind of problems to address and advance in AI foundations. So here I will give a few descriptive examples and to show our progress in the approach. So first of all, talking about intelligence. Well, this is the basic functionalities that we wanted to apply across all the test beds and situations. So what is the intelligence? Essentially, we wanted to gain insights into system operation. We like to respond in the forencing and inferencing segments. Based on this, we are able to enable transfer learning, continuous learning, kind of handle the situation corresponding. Well, I actually grabbed two examples from this pillar representation. For example, Vahi has been working on causality and deep learning. Well, and I also presented about the hierarchical OOD detection. I also have small labels to show which pillar this and slice and grab from. But again, these are general AI methodologies and can be applied to different aspects and optimize them based on the application. Okay, so go back to my own work in hierarchical OOD, for instance. And previously, I mentioned that existing OOD methodologies and couldn't provide very good interpretabilities. It couldn't interface on the OOD examples. And of course, there's no ability to distinguish fine versus coarse grain data, and having difficulties in why we scale up the problem. So I mentioned about our approach in hierarchical OODs. It has a class and structure. So the advantage over here is we can trace the decision paths and then use this information to evaluate it, data, and also our methodology. For example, there are some common error cases, and whether the OOD detector is systematically produce incorrect data and situation, or the OODs have facing under-predicting or over-predicting due to poor collaboration of the data. I also mentioned the possibility in the real setups, like across different branch, we can decide the coarse versus fine selections. So with all these setups, again, it helps us to interpret it, the detection procedure, and then again, apply back to the applications of interest. My second example is in talking about the collaborative or interactions across different perspectives. So although we're talking about efficiency, heterogeneity, and securities, and while we address real problems, and you couldn't just target one metrics and ignore others. In reality, we kind of putting and trade off a different perspective. Right? For example, Professor Song Han at MIT have been working on tiny ML on device learning, and of course, efficiency at the edge is extremely important. But we are doing this and across many, many edge devices, and privacy is a big concern. So a lot of people utilize federated learning to protect the data at the edge. And when we apply such kind of collaborated network-based communications, then connectivities, the data in transition, need to be considered. And of course, and while we're developing this, and we're trying to prune the edge data to improve in training efficiency, we also apply the mask schemes in order to reduce the data in transition, right? But essentially, during the real work, so we're concerned about the trade-offs in between different. For example, how can we trade off the security versus the efficiency? A lot of the security-related tasks, in fact, can trying to modify the training processes. While we are doing this and improve the security levels, and what happens is the convergence becomes harder, and the performance of the classifier, object detection, and so on and so forth, and get worse. And here I given 3 examples: universal training, federated learning, and the differential privacy SGD. And all these actually showed harder convergence. All these actually showed degraded performance. Well, there have been a lot of case optimizations to address and, explicit situation and setup. But I guess more generally, we are curious, and is there a way to analyze the convergence of these and training algorithms in a unified setup? So let's go back to this and optimization situations. And one observation we have, in fact, is in all these training methodologies, and they're trying to apply perturbations during the training process. Perturbation can be applied to the input data. They can apply to the loss function during the. So we define row heat over here to represent the perturbation on the input. For example, for federated learnings, every training epoch, we pick a portion of an edge devices, and each edge devices could have a different data distribution. So as you can see, the data distribution at time t, the distance of this and from the distribution of the target or the overall data, this is represented by the perturbation on the input. Similarly, when we're talking about adversary attack training processes, and we intentionally injecting some perturbations on the input data, and of course, ROTI can serve the same purpose as well. Okay. Well, for DT SGD methodologies, and we use a Sakai-T to measure the distance of grade descent of the loss function at T versus as a target loss functions. Well, with these two definitions, and we can conduct a convergence analysis in Ender SGD optimizer. And on the right-hand side, you can see there are 4 terms. First 2 terms are same as in standard SGD training, but last 2 terms were introduced by security protecting trainings, and we mentioned. Well, the existing of these 2 terms then explain why these training methods and have a poor convergence and why they have a poor performance. On the other hand, more general speaking, and with this in general setups, and we are able use this to help us to optimize and training methodologies and the trade-off, the training efficiency and the security level. Well, the last example I like to give is efficiency. In fact, for anyone working on the systems, and efficiency is always the key. Well, Suman talking about ChatGPTs, and right, the model becomes extremely large, and then how to getting these models to the edge, how to have a more efficient implementation becomes important. And when we're talking about efficiencies, and the team work on different levels. For example, it could be on the computing systems and presented by Lisa early today. And also it could be related to the operations and data flows and presented by Maria early today. From algorithm levels, and in fact, people are really interested in how to develop effective and deep learning models. And the neural architecture search has been a very important approach. So when we're doing neural architecture search or AutoML, we can trace back to the history. Like years ago, when computing power was not that significant, people start from manually designed model architectures. That time, it's purely based on the human's understanding. And when we getting more and more automation in model generations, and still, since the computation is very limited, we're still trying to apply some human bias and during the search when developing the search space. So one example is a lot of the NAS methodologies in novel days and still based on the MobileNet V2 basic block, because this is still seems the most efficient blocks and developed. However, as the previous pillar and show in our use situations, we do not only handle the image data. We handle multimodality data. So the model itself need to address and such difference from the data, and therefore reflect on the model development. In other words, when we're developing these models, we need to expand the search space and consider the heterogeneity from the data and induce to the model development. This is our work and related to the SRAC and SuperNet. It was built for the recommender systems, but as you can see within the blocks, we tend to create the pattern to handle dense 2D data and also sparse and 3D outputs. Very importantly, through these structures, and we do build a lot of interactions and cross in different components, enhance the performance. I do not explain the result over here. I guess then another important observation is that as we address those heterogeneous data, and the ability to rank and distinguish the quality of AI designs becomes very, very critical. Well, again, if we're just talking about the dense versus the sparse situations, and I illustrate in a predator-based ranking mechanism over here. So what we propose is by combining the priors from different types of the training data, we are able to provide a better prediction and use it to guide the search space path selection. So in this way, we can produce an optimal model in a faster and more efficient way. So at the last, just there's no time to give more examples, but at last, I kind of grabbed this strategic plan page and from overall center. Again, for AI research, we primarily focus on the 4 task forces on different perspectives. Our thrust and serve were different pillars, considering the different test banks and scenarios. According to this, and the center, all the team members and developed 9 focus areas. What I really wanted to emphasize in here is AI provides the foundation of all these application domains. As in turn, these applications help us to deepen the understanding on AI models we need to produce and helps us to advance the AI foundation eventually. So such collaboration is extremely important. This is the end of.
Done with. Yeah, I've been monitoring the chat. So now it's time for our lunch break and executive session 1. So you guys are free to do whatever order you want to do that in, lunch first, executive session, or vice versa. It's up to you guys. Lunch is served over out here. The poster session is getting set up so that you can get your food and mingle. And then okay, yes, students, there are first, second, and third place poster prizes. And the way we're going to do this is everyone gets a vote. When you pick your top poster and you see the person at the registration desk, and they will mark the poster you're voting for, and the 3 posters with the most number of votes wins. Very simple. Very similar to last year. But only 1 vote per person. All right, thank you. And Zoom participants, we will break until 2:30 p.m. for the strategic impact presentations. Open them. We could. All right, good afternoon. I am Dr. Shawnee Daly. I'm joined by Dr. Daniel Limbrick and Aaliyah Carter. We are part of the Education and Workforce Development and Broadening Participation team. We are not joined today by Sandra Roach, which is here to my right, or Dr. John Kelly, who are also part of the team. All right, so I want to start off by announcing a couple of new additions. One, Sandra Roach, that I just said, she's joined us at research. She has a background in electrical engineering. She is the author of a book called STEM Navigators, Pathways to Achievement in STEM. She has 15 years of math and science tutoring experience, and she was also a high school teacher. Then Aaliyah Carter, she's joining us also as a research scientist. She has 15 years of STEM teaching experience in both informal and formal environments. She was the founder and director of the Science Engagement Department at the
If I play this, that's
and she served also as a 4th through 8th grade math and science teacher. So really thrilled to have them on board to support a lot of the activities that we're doing, and also grateful for the Duke Center for Computational Thinking for supporting us with extra funding. All right, so just as a reminder of our goals as stated in our strategic plan. So goals 1 through 3 really follow the same format to increase awareness, interest, and knowledge in Athena-related themes for K through 12 students, undergraduate students, and graduate students. Goal 4, to actively involve postdoctoral researchers in Athena-related research. Goal 5, to increase understanding and application of identity and related topics into Athena-related research themes. Goal 6, broadening participation of underrepresented groups in Athena-related research themes. So you'll notice that we are doing education, workforce development, and broadening participation together. That's because we consider them as tied. We're trying to think about education and workforce specifically in the space of broadening participation. All right, so this is the Athena ecosystem. So this kind of holds all of the education and workforce, the broadening participation activities that we're doing right now. So I'm going to go from left to right. I took away the animation since it seemed to be issued earlier, so I apologize for all the stuff on the screen. But for K through 12, and I'll go more into this in just a moment, we have Spark workshops, after-school programming, summer camps, as well as academic year internships for high school students. Undergraduates, they're participating in REUs during the summer, as well as academic year research. I'll cover some of those numbers in just a moment. For our graduate students, we have a graduate, actually this is for undergrads, we have a graduate boot camp to introduce them to graduate school and to them about writing research statements and whatnot as far as the process of applying. They're doing laboratory research with our PIs, and then there's been some development of AI ML modules. We have the Athena Postdoctoral Research Program, and then for our faculty and staff, we have the 3C Fellows Program that Rajeshi and Aaliyah I know are participating in now, and then we have Inclusive Excellence Professional Development. That's something new that we're starting this year, where we're going to be providing training for our PIs to get introduced into inclusive. All right, so I want to expand a little bit on the ESLI goals.
So embedded STEM labs initiatives, again, these are activities targeting our K through 12 space, right? So in general, like the overall goal is to broaden participation in STEM, to build capacity for K through 12, as well as our nonprofit partners that I'll talk about in just a moment, to strengthen equitable research practice partnerships, and to think about STEM justice. All right, again, apologies for everything on the screen at one time, but a little bit more about this model, so going from left to right. So for our engaged partners, which can be faculty, university students, and alumni, as well as industry partners, we want to offer for anyone in Athena Inclusive Excellence PD, research and evaluation support for their educational activities, logistical support. So if you, as a faculty member, want to do something in the K through 12 space, we can connect you with our partners, right? We can also arrange you to come in certain spaces as far as like what that activity is going to look like, and we can also help with translating research into educational activities for people who don't necessarily have that expertise. And again, we can make those partnership connections. And we can do that for faculty, we can do that for students, and we can do that for industry partners as well. We already have a number of community collaborators. So Knox Street Studios is local here in Durham. Inspiring Minds actually has 5 chapters. There's a local chapter here that I'll talk about in just a moment that one of our faculty has already worked with. But they also have chapters in Philadelphia, New York, 2 in Ohio, and then one that I'm missing that will come to me as soon as I finish talking. And then we have the STEM Early College, which is in, finally, for our nonprofit partners, we really want to think about not just coming in while we have grant money, but also really how do we expand capacity for them while we're interacting with them. And so we offer STEM professional development. I'll talk about that in just a moment. We're helping them think about technology infrastructure and what they need to use. We have logistical support, so matching the nonprofit partners with our PIs or with our students who are involved in the initiative. Logistical support, again, like we're coordinating and setting up sessions. So if it's a 5-week session, if it's an 8-week session, if it's a Saturday session, we'll do that logistical. We'll actually work with them, our partners, to create curriculum. So we don't just want to come in with a made curriculum and say, hey, we're going to do this. We actually work with them to say, what are your needs? What are your students' interests? What are the things that you want to talk about? And we'll actually work on that curriculum with them together, and then we'll match them with partners. So again, our engaged partners, like students or faculty, we're matching them with these nonprofit partners. All right, so our community collaborators that I mentioned already, Inspiring Minds, Knox Studios, the Whitaker Project that I didn't mention a second ago, they have these spaces called Be Social that are community spaces that you can rent out. It's actually free, and you can do any kind of event you want as long as it's free to the public. They have locations in Houston, Greensboro, Charlotte, New York City, Chicago, thank you, Atlanta, Baltimore, and 2 in Pittsburgh. I'm there. All right, so I'll turn it over to Daniel for a moment to talk about the year-long high school internship.
Yes, so we are working with the STEM Early College at North Carolina that is on our campus. So they have a requirement of having a year-long senior internship. That can be at a company or it can be in a research lab. What that means for us is through the partnership that they agreed to with Athena, we then have 6 to 8 high school students in our lab on a weekly or biweekly basis. More recently, it's been virtual because of the pandemic. So I'm excited about when we come back in the fall. That'll be the first time in a while that we are doing this in person. The goal is to get students excited about AI, autonomy, edge devices. And so we have a couple of projects that we work on. One is we have the students build their own self-driving car. So they use a microcontroller device, and Arduino Zero, Raspberry Pi Pico. We also had them use a RISC-V device before to then run a self-driving car algorithm. They do that with, for the most part, basic sensors, but also potentially with cameras. And at the end of that, hopefully they have a little bit of experience with that part of it, and they get more excited to where they want to do that in the future. So an example of that, so one student is currently in the room who was an alumni of that program, and he's now an undergraduate at North Carolina Rubio. So he is now working on some of the topics that we work on in Athena. I also have 2 students who were previously a part of this program that are joining Athena for an REU over the summer. So it really is something that kind of gives them exposure and gets them excited about becoming an undergraduate researcher and hopefully a graduate researcher. So the same thing is true for the other project that they can potentially work on, is using the game Flow Free to map out an automatic solving algorithm for that puzzle. We have a Python challenge and an ML challenge for that. And so there are just multiple opportunities to take Athena's research and package it in a way where we can introduce high school students to these topics as well.
All right, so this is another community partner. Daniel, of course, was working with NCAA STEM College. This is with Knox Street Studio. We just wrapped up an 8-week session with students where they were learning programming, they were learning Makey Makey, which is an invention kit, and they were designing wellness spaces, and they were thinking about computational ways to express their ideas. And so really getting students early introduction, right? So this was twice a week, so more deeper exposure they were able to have rather than like a 1 or 2 hour session. And again, we worked with the partner, Knox Street, to build capacity with them. Had meetings well before we did it in order to create the curriculum as well as teach them about how to use the materials as well. Professional development, so this is with our partner Inspiring Minds in actually Warren, Ohio, and a local chapter here in Raleigh-Durham area, where we were doing the professional development. We did 5 of them, some virtual, some in person. We actually brought them here for 2 days in March, and they were, again, learning what we're going to use for a 6-week summer camp that's going to reach over 400 students starting June 20th. So Aaliyah and Sandra will actually be going up there for the summer to work with those students and their staff. But again here, the idea is not that Aaliyah and Sandra go in and they do their thing and they disappear, right? We want to work with the staff so that they can continue those activities with or without us. And so that's why we were doing this professional. Fabulous Fashion, this is with our partner, the Whitaker Group in the Be Social space. We were doing wearables, so they learned some bit of computer programming. They also learned some circuitry, right? So introducing them to both hardware and software aspects, things that are like fundamental things, right, that could get them excited about Athena-related research. We did one so far, that was March 25th. We have another one coming up May 13th, and they were excited enough that we're expanding to do 9 more in Charlotte next year, and we just learned 2 days ago that their Atlanta and Houston chapters were jealous, and so we're figuring out how to do some things. We're going to find some funding so that we can do some things with. So we're really excited about this initiative, and again, continuing to try to be value added to nonprofits that may or may not offer these kind of activities to their students. Tingjun Chen, who's in the room, one of our professors. Again, what I was saying with our model is that we want to work with professors who want to connect with nonprofits, right, and to help translate. Tingjun already had a lot of work done from his Cosmos work that he did at Columbia, so there wasn't a lot of translating that we had to do, but we did do a lot of the logistics of making sure people were training, making sure that the sessions were set up, connecting with the community partner, and then Aaliyah and Sandra attended the sessions and were the facilitation of those activities. So we'll continue to do things in the fall with Tingjun. We're also hoping, in the future there will be other professors who will want to connect with our partners, and we'll also expand our partners. We also experimented with undergraduate engagement in education and workforce development. One of the things that I found in my own research is a lot of minoritized and women, when you engage them in more educational or things that have a social justice theme, that they tend to stay more in the field. And so we want to work on our end when we're doing education and workforce development, broadening participation activities to engage undergraduates in this. We had a student who did an independent study with us during spring 2023. She'll also be helping to facilitate a summer camp with our partner here in Raleigh-Durham, Inspiring Minds, for a 6-week summer camp. Well, she'll have, I think it's twice a week for an hour, she'll actually be delivering STEM lessons. For after K through 12, we'll have 5 summer REU students, 26 students during the academic year. We've had the graduate boot camp will be happening again. We're going to do 2 sessions. One will be online in July, and then we'll have another one in September that will be in person, where they'll be visiting both Duke and North Carolina A&T so that they can get the experience of both campuses. For our graduate students and postdocs, we've had 6 master's students, 29 PhD students, 4 postdocs that are all working, of course, with our PIs. There's been some curriculum and module development. So Nita Farahani's team developed and improved a course called Let's Talk About Digital U that will be broadly disseminated, and then previously developed modules and then further tested them with, well, those will be broadly disseminated as well. Another team is working on the AV Stack open source. It's a reconfigurable software platform for AV design, implementation, test, analysis. Miroslav can talk more about that if y'all have questions, because I'm not. And then at Yale, of course, Principles of Computer Design modules. Again, for faculty and staff, we want to offer opportunities to increase understanding of identity, both for the way that they might mentor as well as how they might think about the content of their course. Through partnership with another NSF grant, we've left spots open for any faculty who want to participate in the 3C Fellows program. And basically that's cultural competence in computing, and it introduces everyone to aspects of identity and then thinks about how policies and practices might indirectly disadvantage certain. With respect to our demographics, we are 27% women. We put a goal in our strategic plan for 35%, so not too far off from that. Looking at our transgender, non-binary, gender non-conforming population, we're only at 1%. For minoritized population, we're at 12%, and then all underrepresented, that's going to put in LGBTQ communities, first generation, and minoritized into one group. We're at 20%. For our K through 12 activities specifically, I was not counting them in the overall demographics. We're 43% women and then 96% underrepresented. That means Black, Latinx, indigenous populations. Some challenges we've had is participant tracking, so keeping up with all the things that all the PIs are doing. This year we developed a shared measure tool so that anyone who's working with undergraduates or grad students can actually track their engagement. And so we'll be rolling that out over the summer. We also had a shift. Initially, we had the idea that we would have at least 7 REUs for the summer. We didn't have a lot of uptake in that, but that actually ended up being a really good thing because we shifted a lot of that funding to hire an associate in research, and that's enabled us to really expand what we're doing at the K through 12 space, and we're actually really excited about what we've been able to do with that because we can really enhance our faculty support, we can really enhance our impact and reach a lot more students while not having to rely on undergraduate student support. And then again, we developed these mechanisms for undergraduate engagement in educational workforce development. One of the things that we've started advertising to students as far as how they might be engaged is to volunteer with an existing program that we already have, to develop their own program, curriculum, or technology, and then to use that with our partners to pursue an independent study for research so they can actually get educational research. I actually had a student, it was tangential, but I had a student who was doing educational research this summer for her senior thesis, able to graduate with distinction. So what do we have looking ahead? As I mentioned, we have the summer camp that's going to be in Warren, Ohio, where Aaliyah and Sandra will be going up there. Fall, we have a Knox Street Studios 5-week session that we're very excited about. We're going to take the lessons learned from the 8-week session and iterate on that design and implement again. Daniel will continue with the early STEM college individual research, and we're talking to him about his free flow and how we might help him do more translation for the curriculum and what that looks like. Whitaker Group, which was our fabulous fashion activity, as I mentioned, they want us to expand, so it's actually more nationwide. And we will continue working with the first LEGO League on judging. For undergraduates and graduate students, we will continue with the REUs, although we've scaled it back a little bit, as I mentioned. Continue to do academic year research, which actually seems bang for our buck, so to speak, and then some capstone development that some faculty are planning. We want to increase the amount of faculty and staff that are involved in the Inclusive Excellence PD. We'll be offering a 2-hour session in May. It is May. About that. This month we'll be offering a 2-hour professional development, but faculty can also participate in 3C, which is much more sustained, but I think it's a valuable activity for all of us so that we can know how to create inclusive environments for our students. And then we want to enhance our dissemination efforts. We really want to think about how we're getting the word out about the work that we're doing. We do have a Twitter account that hasn't gotten a lot of activity, but luckily Sandra, who's on our team, has a lot of experience with these things. Moving forward, she'll do a lot more developing that strategy as well as thinking about how we're rolling out and how we're talking about what we're doing. We're thinking about doing something called Science in a Minute, where we come around, we interview all of our different PIs to talk about what they're doing, and then we translate that so that people so that we can showcase the great things that faculty are doing. And then we actually set up now already Instagram for some of our broadening participation, just because that's really where we're seeing students engage. The adults are really on Twitter, and then the older of us are on Facebook apparently. But the kids, they're all on Instagram. So we're trying to, or MySpace, yes. That's great. So we're going to pause here, and I think we have like 30 minutes for questions if anybody has questions. All right, well, y'all make our job easy. All right, thanks.
Okay, so based on the agenda, we will move to the next fun part, which is going to be meeting with institute students, and you will get also the chance to look at the poster outside. I know you have lunch, you probably don't have time. Here, right? Yeah, I think for the faculty members, who are not participating, they're free to release, right? But they're coming back. Okay. 5:30 for the leadership team, but not for all the faculty members. No, for 1 hour. We're actually going to start at 3:30 to 4:30 with students. Okay, so based on the agenda, basically provided by National Science Foundation, I think for the students, who are supposed to meet with, the NSF evaluator, you're going to stay. For any other faculty members, who are not in the leadership team, I think you're released. And you will coming back at 7 for dinner, I think. That's it. For the leadership team, you'll stay, yeah. Oh, that's right. Right. Oh, okay. So, okay. I think for the faculty members, for our PIs, you may want to stay talking to our evaluators. So, yeah. And then 3:30 we'll move to the students. And at 7 p.m. we have a dinner here. So, yeah.
Can everybody hear me? All right, I'm taking control. So we have scheduled time at 3:30 to meet with students for 1 hour, which is more than enough time. But if there are any faculty who aren't part of the leadership team who want to talk to us, have any questions, want to tell us about what they're doing, you know, any of that stuff, now's the time. We have some time. So let's treat this as schmoozing time, and then at 3:30 we'll kick you guys. Sound good? Okay. Schmooze, go.
I don't care about the Zoom either.
Okay.
Right now.
A break?
The more important thing is the students.
Yes.
So, the faculty don't actually have to accept for dinner, work on the responses, or you can just show up at the science workshop tomorrow morning. They're not coming tomorrow morning for the.
They can if they want. Everyone's welcome, okay, so just to clarify, we're a half an hour early now, so we're going to have just a break, mingling time now. We want to stay to the same schedule, that the original schedule. So this is a half an hour break, and then after this, the students will be in here
With the leadership.
with no.
With the
Yes, with the NSF and site visit team. The Athena PIs have to go elsewhere. And then immediately after your student meeting, you will have your executive session, and NSF will. And then we will all meet back here in this room. NSF and the leadership team, other PIs are welcome to come. There's, like I said, there's no secret things going on here. So, it's secret, yeah. So, everyone is welcome to join back here at 5:30 p.m.
And stay.
And then, yes.
Have dinner for students.
Then we split up again, and the NSF team goes back to the hotel for dinner, and the rest of us stay here in this room for dinner and writing our responses. So it's not going to be a fun dinner, it's a working dinner. There's no entertainment or anything. I don't want anyone to have expectations.
And then, after your meeting with NSF, you're free to go. You're no longer required to stick around. Students. Faculty, the leadership team has to be here for the response from NSF, but anyone else, any other faculty are also welcome to hear the questions from NSF, and also to stay for dinner if they want to help us. But if you stay for dinner, you're going to have to help us work on the answers to the questions for NSF, because it's not going to be just chit chat. And then tomorrow, very important, all the faculty in the Athena need to be at, they should come, the leadership team should be here to hear the, to respond, to give our answers to the leadership, to NSF, but most importantly, all the faculty here in the Athena Institute should make sure they go to the team science workshop that starts at 11 a.m. and it's in a different location. It's at the Tobacco Road Sports Cafe in Durham. So that should be actually a fun event, a useful and fun event. Is that clear?
Students, please stay for the student meeting, okay, which will be in this hall right here.